All right, so people said last time the talk was like pretty heavy. Um, and like honestly, like a lot of what's gonna happen in this talk is like only somewhat related. Because like there's lots of different ways of viewing spinners, but I figured I would do a quick review of what we did last time. So I defined this P plus and these P minus projectors. So if you remember, a projector means when we square it, it just goes to itself, and that's true with P minus as well. And when you have projectors operating on, the result is what is called an ideal. So this projector, when you act on the left, you get this left ideal, which is matrices that look like this with only the first column non-zero. And when you act on P minus from the left, you get this left ideal. It's this column. And then when you act on the right, you get this right ideal with the first row non-zero. And then when you act on the right for P minus, you get another right ideal, which is the last row non-zero. And some I guess one definition of spinners is that they're ideals in your algebra, basically. So I think this here corresponds to like a 2x1 column spinner, like a Pauli spinner with the two components. So did people? I know I threw a lot of definitions, but how do people are people still grappling with this definition? Like, is it really confusing? Okay, I know Slava's been like thinking about spinners more than probably the average person here. Does anyone else have like feelings on this definition of spinners being ideals?
Well, this seems quite a logical construction, all of these, but where did this actually connect? We
Yeah,
talk about
so I talked a little bit about this. Like, I'll answer your question in a couple slides. I'm just going to review some things first. So, if you remember, these are the 8 elements of what we said was the Clifford algebra CL30. So we have like the scalar, the vectors, the bivectors, and then the trivector. And there's some repeats in the results here, like these two, and I think like these two here. So this ends up only being 4D, and then with P minus, it's another 4D. So like when you use these projectors, you split the space into like two. It's 8D, but you split it into a couple of 4D spaces, and that's where the spinners live. And like I showed that these are not very scary in terms of the matrix form. They're just like they just give you like the first column. And again, this is like a column spinner, like 1 and 2. And yeah, and I said that these were like the spin up and spin down states. So like you could have a state that's like a linear combination of up and down, where these are complex numbers. And you can start like, figuring out what the probabilities are using inner products. So this would probably give you just alpha, and then you'd have to square that to get the probability. And I think these are just these matrices. And then I think this was the really important part, where I showed how sigma z acts on them. Because like this is how you sort of get the expected value of spin in sort of an intro to quantum mechanics class. So I showed that when sigma z acts on up, you get a plus, and that'll give you like a plus 1/2 or h bar expected value. And then when you operate on spin down, you get a minus which will give you like a minus 1/2 h bar expected value. So this was sort of why it connected back to our original definition of spinors, is because these things, even though they look really weird, and like the way of getting them was really abstract, like we had to like talk about projectors and all that, but they end up behaving exactly like the up and down states from an intro to quantum class. So does that answer your question about why these things matter? Or are you still a bit confused?
Yeah. I get it now.
Yeah, and like this is like really unexpected for me. I was not expecting this to happen, but I read enough notes where I came to that conclusion. And yeah, so we said that like the spinors, like these things, they live in the Clifford algebra, but then the spin group, like the rotations operators, also live in the same algebra. So spinors and rotations operators live in the same algebra, which is a bit interesting. Now, I think Slava and I have been very confused about this. I've just showed you the ideal definition of spinors, like they're ideal members in a Clifford algebra, like you project them and then the results are spinors. There's also this other definition called the Hestonese definition, where it says spinors are even grade members of a Clifford algebra, which seems like a different definition. So I'm just gonna back up and see if I have the slides in order here. Okay, so I'll talk about why these. I'm just gonna mention a couple things. Sorry, go ahead. Question.
Oh yeah, it was about minimal ideas. Are there something else
right.
than minimal?
Yeah, so a minimal ideal means there's no ideals inside of it. So if we have like an algebra, and then we have an ideal, if there's another ideal inside of it, then it's not minimal. So like only, yeah. And I think to make this more concrete, this projector here, this would take x, y, z and project out x and y. But this is not a minimal projector because you can write it out as an x projector plus a y projector. So basically, a minimal ideal means you need a minimal projector that cannot be written as a sum of two projectors. So I think this projector is minimal, which is this matrix here, because you can't write it as a sum of two projectors. So, and those give you the minimal ideals.
Okay, cool.
Yeah.
Yeah, I just wanted to say that it's the same process, kind of analogous one, which you have in the representation theory when you are building your like simple representations, right? So you have kind of like atomic representations, so the minimal ideals will be like the atoms inside the structure of the algebra.
Yeah, they're like the most basic ones. Because like I think if you put two, yeah, like you can sometimes break up ideals into smaller ideals. So yeah, like the minimal ideals are the very most basic ones.
Yeah, and if you will meet a group theory representation, they will be called their normal groups. I think that's the right name. But the idea behind is the same, actually.
Yeah, I'm a bit rusty on that, so I can't really speak to it. But okay, I'll take your word for it.
Yeah, we have seen those in Road to Reality. Actually, I think it was chapter 11.
Okay. So I wanted to like talk about these two definitions and how they're connected, because like it seems like every other paper Slava and I find they like switch definitions. So I wanted to bring up a fact. So if we have a unit vector n that's like a normal vector, or like a like unit 1 normalized length, we can get a projector like this, and like we did that with sigma z. Sigma z squares to 1, so it's a unit vector, and that gave us p plus. And there's kind of this magical property, this is from Crystal and Mackenzie's thesis, she calls it the Pacwoman property. So basically, if you have a projector defined with n, and then n multiplies onto it, the n can basically disappear. So I'll show you with sigma z why that happens. If I multiply by sigma z and put it inside, then I'll get sigma z here, and then I will get sigma z squared, and that goes to 1. So you can see I just ended up with what I started with. So basically, when a projector is defined with some unit vector, it kind of eats up the unit vector and it just kind of disappears. So she called that the Pacwoman property. And I'll show you why that's useful. So basically, here you can see this is like an 8-dimensional Clifford algebra element. So we have the scalar, vector, 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 bivector, 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 trivector. And she is going to act on it with P3. So that's just this vector here. And remember, P3 can make like E3s disappear. It can make the third vector disappear. So here an E3 gets multiplied on here. So actually, I should say it can either make an E3 disappear or you can add new ones on, right? Because like P3 equals, like you can add as many like E3s as you like. So when you multiply by P3, you can put E3s or take them out wherever you like. So here she's putting in E3s. Here she's actually getting rid of the E3. Here she just keeps it as it is. There she keeps it as it is. And then I think here she gets rid of it. And by adding and getting rid of these E3s, she's able to write everything as just a scalar and I think 3 bivectors. So a scalar and then the 3 bivectors. These are like the even grade members because they have like 0 basis vectors or 2 basis vectors. The odd would be like these because they have like 1 or 3. So do people follow that? Basically, because of this Pacwoman property, when you use the projector, you can sort of rewrite everything in terms of even grade members. You can sort of change an odd member into an even member by either taking away an E3 or putting an E3 in. Is that okay with people?
One comment, I don't know, this perhaps has no real connection, but this has some resemblance to the combinatoric logic and lambda calculus, where you can apply some functions to the forms and get either the same result or do something like you presented here.
Yeah, it's been a long.
My mind.
It's been a long time since I've studied lambda calculus, so I can't comment. But I think Clifford algebras kind of have a combinatorial flavor because, like, you have like the scalar, then 3 vectors, then 3 bivectors, then a trivector, and this is like I said last time. This was like 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. So yeah, there's kind of like a combinatorial flavor to it. But basically, the reason I bring up this Pacwoman property is because, so I have this chart I've shown you before with the 8 members getting projected down. Now, basically, you'll notice there's some repeats, like this and this end up being the same. That's because they differ by a sigma z. Or like this and this end up being the same. That's because their elements differ by a sigma z. Here and here are the same. Again, those elements differ by a sigma z, and then the other 2 also differ by a sigma z. So basically, if elements differ by a sigma z because of this Pacwoman property, the projector just kind of throws away the sigma z and doesn't care. So according to this, because of the sigma z Pacwoman property, 1 and sigma z are almost indistinguishable. They project down to the same thing. Or like xy and xyz are like the same thing because the projector just throws away the z part. So yeah, so basically for a projector defined with sigma z, factors of sigma z do not change the projection results, and that's because of this Pacwoman property. So yeah, I tried to like highlight like the ones in blue project to the same result, the ones in green project to the same result, in the black they project to the same result, in red they project to the same result. So the reason why there's a sort of an association between like these elements here and like the projection results and the Clifford algebra's even elements. So like, for example, the black terms, I can pick 1, which is an even element to represent them. Like sigma z is an odd element, but it's like kind of the same thing as 1 because the sigma z's just get tossed away. Or like, this is an even element here, y, z. That's kind of like the same thing as y because the sigma z gets thrown away. But basically, this 4-dimensional space, I can choose even dimensional elements to represent the projection results, basically, because the odd dimensional elements, I can always make them even using an extra factor of sigma z. So when people say spinors are like even grade, I apparently don't know how to spell grade. Even grade members of Clifford algebras, it's the connection to this minimal ideal definition is that when you project even grade members, you get the full set of spinors, basically. Like you have a 4-dimensional space. Like this even dimensional space is 4D, and then there's like no repetitions when you project them down. So you get like this would be the first basis vector, and then this would be the second, third, and fourth, and those all come from the even grade elements. So yeah, that's sort of the connection there. How do people feel about that?
I feel happy.
You feel happy? Because we've been sort of confused about this for a while.
Yeah. And it seems to me that like it's only feeling currently, but I think we have an isomorphism here. So we can associate even element with the corresponding projection by some fixed projector.
Yeah, so like in the minimal ideal definition, like sigma x, sigma y, p plus would be the spinor. But in the Hestonese definition, I guess you just leave out the p plus and you just say the even grade element is the spinor. So that's kind of the connection.
Yeah.
You either include the projector or you don't. That's the difference between the two definitions. So maybe Slava, that means more to Slava because we've been confused about that for a while, but that's something that came up. What else? Yeah, so this is something I mentioned. There's like 4 ideals, right? There's like the row, there's like the left column, there's like the right column, there's the top row, and then there's the bottom row. I can't write this, B and D. So there's also 4 types of spinors, and I don't understand this yet, but I've seen in the literature there's 4 types of spinors that transform in different ways. So here we have like a matrix lambda, complex conjugate, here we have the transpose inverse, and then here we have the complex transpose inverse. So my kind of theory is that these 4 spinors are the 4 ideals, but I haven't really connected that yet. And I think this matrix here is called like the spinor metric. And I think I'm this is like I'm kind of making assumptions here. I think this is a contravariant spinor. No, go back, please. I think this is a contravariant. I think this is a contravariant dot. Stop doing that. I think this is a covariant, and I think this is a covariant dot. This is my theory, but I haven't proved it yet. And I think the metric can basically like raise, like they call this epsilon, like alpha, beta. I think it can like raise or lower an index, kind of like we've seen in tensors. So this will become like a covariant. You change a contravariant spinor into a covariant spinor using this spinor metric. Again, I'm still kind of fuzzy on this. Slava, does this make any sense to you? Like, have you read about this, and does this mean anything?
I have seen those. That's true. And your hypothesis seems viable to me. So it needs further investigation.
Yeah, I need to look at it more. Yeah, so like I've seen like, because like with tensors, there's usually like two indices. It's like a contra, like M contra variant and covariant tensor. Like the Riemann curvature tensor from relativity is like a 1-3 tensor because it has one upper and three lower indices. But with spinors, they actually have four. So they have like the normal upper, then like the dotted, or I guess primed here. Then they have like the lower and then the lower primed. And then this is one source. This is another source. It writes the four indices like this. So it has like contravariant, covariant, contravariant. I'm not sure what all these symbols mean, but you can see there's like four types of indices. There's the upper dot, lower dot. What's this? So like it says like Pauli vectors, like if you remember those like 2x2 complex matrices, that was like x sigma x, y sigma y, z sigma z. This is basically saying these are all like rank 2 spinors with a contravariant index and a contravariant dot index. So again, I don't understand this yet, but it's trying to say that like vectors, Pauli vectors are like rank 2 spinors because they have two spinor indices. And yeah, so like my main question was, do these four ideals correspond to the four types of spinors? And again, so I was thinking like this is the upper 1, 2. This is the upper dot 1, 2. I think this is the lower 1, 2. And I think this is like the lower dot 1. Lower dot 1, 2. Again, this is my guess. Still need to think about that. So I think I'm gonna get into the actual talk now because that was just review of last time. So I don't think I'm gonna talk about ideals very much coming up, so you can sort of forget about them for now. I will also admit I got a bit tired of making these, and I did a bunch of copy pasting from Wikipedia, so the slides might be a little bit lazier this time, but I was just getting kind of tired of making everything. So I think I'm going to talk about Lie groups and Lie algebras next. So that's something that came up in the book. Do people feel like they understand Lie groups and Lie algebras, or are they still kind of fuzzy on them?
It's fuzzy for me.
Fuzzy? Okay.
Remember
okay.
the terms.
Okay, so hopefully, do people know what SO3 and SU2 are? I know I threw those around before, but does that mean anything to people?
About the symmetric groups, right?
Yeah, so like SO3 is like a rotation matrix in 3D. They generally look like this. I think this would rotate Y and Z. And then SU2, those are the 2x2. The reason it's called SO3 is because it's determinant 1, determinant plus 1. And that means all of its columns are orthogonal to each other. So if you took the dot product of any of the columns, they would give you 0. And that means that its inverse, like if O is a member of SO3, then its inverse is its transpose. So to invert a rotation matrix, you just like take the transpose of it. So if I wanted to invert this, it's basically just taking the signs and changing the plus to a minus and the minus to a plus, because I'm just transposing it. And then SU2, I forget exactly what they look like. Is it like this? Basically, instead of their inverse, if U is a member of SU2, their inverse is not the transpose, but the complex transpose. So that's like you complex conjugate and then transpose. The 2 mean 2 by 2.
In the chapters, current chapters in the book, Penrose talks about the symmetric break. So is it related to this SU2 and the thing you last talk?
Sorry, could you repeat the question? I didn't quite get it.
Okay, so in the book on the chapter 25, I think,
right.
Penrose talk about this SO3 and SU2, and in SU2 he mentioned the disastrous symmetric breaking. So is it related to the last thing you told?
Did you say disastrous? I didn't catch what you said there.
Yeah. Well, it was artistically said. But anyway, many symmetric break.
Well, like I know that like the relationship is that SU2 is like the double cover of SO3, so we're gonna see what that means.
Yeah, I can answer that. So actually, symmetry breaking isn't connected in kind of I think anyway for this SO3 group. So I assume we haven't seen SO3 in chapter 25, but SU2 can be interpreted as 4 bosons. We have like 3 weak bosons and 1 boson for the electromagnetic force. So that's how it is used there in the like electromagnetic weak theory.
Yeah, I'm not very up to speed with like the standard model and actual physics, but this is mainly going to cover the math, and maybe we can talk about the physics.
So it's more related to the chapter 11 from Penrose, actually. And also I wanted to say that in SU2 matrix, you need to have a minus near B star.
Ah, right there?
Yeah, now it's
that
correct.
Makes sense, because then they'll get the plus sign on the determinant.
Can I read a short sentence from the book? It's 25.8. It is the last discussion there.
Sure.
He says it is less clear to me now how, though Penrose says me, in the conventional attitude to the standard model, the group SU2 can be taken actually as a Gauge group, Cox group, while being so severely broken. So, and some might think that this SU2 as reflecting some kind of hidden symmetry, and so forth.
Yeah, so like I know that like in the standard model, it's usually like U1 cross SU2 cross SU3. I barely know what this means. I know this is electricity and magnetism. This is like the weak, and then this is the strong. So I guess, and the weak force has like a broken symmetry. So maybe SU2 is related to the broken symmetry somehow, but I don't know how yet. Like I'm not that far ahead.
It's related to it by using the Dirac equation. So using the Dirac equation in spinorial calculus language, basically you will have the Dirac spinor interpreted as 2 Weyl spinors. And those 2 Weyl spinors will give you a picture of a zigzag motion. So you will have two particles moving with the speed of light for any kind of a particle. So like electron or W plus boson or Z boson, they will give you those zigzag picture. And for those zig and zags, you will have antisymmetry in terms of the weak force. So you will have like interaction only with one particle from the zigzag picture. I think it's zag, or I don't remember the correct one, but it doesn't matter actually. So, and that's what is called like the symmetry breaking, because in reality you do not have the symmetry, SU2 symmetry for the weak force. It was there at the place long time ago, because that symmetry means that you have like a potential to choose any four kind of primordial particles from that primordial soup you had in the Big Bang times or something for like to be used as gauge bosons for the weak force. But we have those fixed already, and that's what is symmetry breaking for me. It seems that the fixation of the bosons after like 10 to minus something after the Big Bang is that like catastrophic, disastrous thing Penrose is saying about.
So a choice was made when the universe cooled down.
Yeah, and that's the problem, because everyone talks about the weak force as like it is a symmetric one, but it is not in reality.
Right, so I think I'm going to give you like the math that might help you understand it, but I'm not going to give you the physics right now.
Yeah, I just wanted to add that you should think about SO3 and SU2 groups just as rotations. So SO3 is a rotation in 3 dimensions, and SU2 is a bit specific rotation, so it's a complex rotation in 2 dimensions. But saying that, I mean that they will preserve like the vector matrix in the corresponding space, or like vector lengths and orientation.
Yeah, if you remember, the Pauli vectors transform using a double-sided SU2. If that was like from the very first talk when I was doing those weird 2x2 matrices, they, instead of transforming with SO3, they transformed with 2 copies of SU2, one in front and one in the back. But anyway, I'm going to get started. So just to refresh your brain, this is like first year, second year calc, Taylor series. So we have cosine, it's 1 minus x squared over 2 factorial plus x4 over 4 factorial minus. So like the minus and pluses keep switching. Cosine, it's like the odd terms, like these are the even terms for cosine. Sine is the odd terms, so we have x minus x cubed plus x to the 5th minus x to the 7th, and so on. And then the exponential one, that's just the sum of all the terms. So these are going to come up later. Now, so what you can do is, if you have a matrix M, you can take its exponential just by using this formula. You basically just put in a matrix instead. So we're going to have a matrix to the power 0, which is like the identity matrix. And then we have matrix to the 1, a matrix squared over, so on and so forth. So e to the matrix might look weird, but it's something we can define using this infinite Taylor series. So I'm going to do something silly, and I'm going to take the exponential of this matrix. So theta is like a variable, and then this is the matrix here, 1 and -1. So we're going to need to get all the exponents of m, like m0, m1, m2, m3, and so on. So I've done that here. So m to the 0 is just the identity matrix. M to the 1 is just the matrix over here. It's just m. So we have 1 and -1. M to the 2 ends up being this. So you could maybe convince yourself if you square m, if you square this matrix, you get like a -1s on the diagonal. And then, this is just 0. M3 is actually just -m1. That's just -m. And then M4 is kind of like an identity, but with this being a 0. Basically, there's a 1 here in the first one, but all the rest have zeros, because M has a 0 here. And then because this is like a 2x2 identity, if we multiply M4 by M, this is kind of like an identity, so we just get M back. So M to the power of 5 is just M to the 1 again. So basically we have the identity at the start, that's M to the 0, and then after this they just kind of repeat. They just kind of go back up here and you just get the same 4 matrices over and over again. So why am I showing you this? So, well, we're going to put M0, M1, M2, M3, and so on. Well, technically it's theta times n. We're going to take the exponential. So we get, I know it's written really small, but this is M to the 0, which is the identity. That's M to the 1, M to the 2, M to the 3, and so on. Now I'm going to add all of these up. So, you add matrices up element by element. So let's take the first element. Here we get 1 plus 0. We get a minus 1, 0, 1, 0. So what you kind of notice is that we get, on the even terms, we get numbers that are non-zero, but on the odd terms, they go away. So you can see we get a 1 from here. We get a negative 1 over 2 factorial theta squared, and then we get a positive 1 over 4 factorial theta to the 4. And then this actually ends up just being the infinite series for cosine. And if you add up all the others element by element, this just ends up being the negative sine series. This ends up being the positive sine series, and then this ends up being another positive cosine. And then because there's a 1 in the first one, we end up with a 1 down here. And this is actually just a rotation matrix in the xy plane, right? Does this matrix look familiar? People could believe that's a rotation matrix. Like it leaves z the same, but it'll leave z the same, but it'll sort of switch between x and y depending on the angle. That makes sense.
Looks like something in 3D programming, I think.
Yeah, I mean, yeah, if you're doing rotations in 3D programming, you'd use a 3D rotation matrix. So yeah, that's exactly what this is. So now the question is, I picked this like seemingly random matrix over here, and I did e to the theta, and somehow I got a rotation matrix. So why did that happen? So here's the thing. So let's say that we have this rotation matrix, and we want to figure out what m is. We're going to say it's the exponential of theta times m, but what is m? We're going to want to figure it out. So let's say that we take the derivative of both sides. Okay? Now, can anyone tell me what the derivative of this is going to be, based on your knowledge of exponentials? You can kind of just use like your standard first year calculus here. You can kind of forget about m being a matrix. Could anyone tell me what we'd get?
So e to the m.
Sorry, repeat that.
M times e to the m.
Yes, right. So m times e to the theta m. So that's exactly right. That's just the rule with exponentials. You just put the coefficient out there. Now we want m, right? So we can do this little trick where we say, hey, let's take theta equals 0. So we'll put theta equals 0 in here, and we're going to turn that into a 0. Now, what is e to the 0?
One.
1, yes. Or if it's a matrix, it's the identity matrix. But basically, this just goes to 1. Or if you want I, the identity matrix. So basically, this gives us an equation to solve for m. All we have to do is we just start with, hey, we have a rotation matrix. It's going to be e to the theta something. And to solve for it, we just take the derivative and set theta equals to 0, and we have an equation for m. So the reason that this ends up being true is that if we take the derivative of this matrix here and set theta equal to 0, well, this cosine becomes a negative sign, this negative sign becomes a negative cosine, this sign becomes a cosine, this cosine becomes a negative sign, and if we go theta equals 0, well, sine of 0 is 0, so those go to 0, and then, so sine of 0 equals 0, and then cosine of 0 equals 1. So this negative cosine becomes a negative 1, and this positive cosine becomes a positive 1. So the reason that this magically worked is that because m is the derivative of the rotation matrix evaluated at 0. So does this logic make sense? I know it's a bit weird that we're like exponentialing matrices, but does the argument make sense? How we can solve for m for a rotation matrix?
This is wonderful. I'm very pleased. Yeah. I didn't know you were covering this stuff, and I'm glad I joined.
Okay. Yeah, so now that we have a procedure for doing this, like we did it for this matrix, but we can do it for any matrix, right? So we just did it for this one, and we can do it for for YZ and ZX rotations as well. And it turns out, so we just saw this matrix here. And then for the other two, basically the rule is when you take the derivative and set the angle to 0, you can just kill, you basically can just put the zeros in the cosine slots, and you can put 1s in the sine slots. That's sort of the rule for doing this. So these, basically when we take the exponential of them, we can get our standard rotation matrices. And we call these generators. So I call this GXY because it's the generator of the XY rotation. This is GYZ because it's the generator of the YZ rotation. This is GZX because it's the generator of the ZX rotation. So you could go through exactly what I did on the previous slide with all these other matrices and it would work out. Yeah, so basically we have these nice little facts where when we exponentiate the generator times an angle, we get real rotation matrices that we're used to from like linear algebra or 3D programming or whatever. Yeah, so I should also mention there's a difference between math world and physics world here. So you'll notice I'm just doing this where I just exponentiate the generator. Like there's no factors of I here, but physicists sometimes like to put an I in there. So basically, you might see the generators with like multiplied by like a minus I in a physics textbook. So this is kind of really frustrating because when you look up generators in different textbooks, sometimes they'll have I's or a minus sign and sometimes they won't. That's because physicists and mathematicians disagree on what the generator should be. But like the zeros and the ones will be in the same places. It's just like an I or a minus I might be multiplied in. So that's just something to keep aware of.
Yeah, I just wanted to say that physicists also like to add some constants that are like h bar over 2.
Yeah, maybe.
Or just 1/2 because those generators, they will give you 2 if you multiply those between themselves.
Yeah, so like basically the zeros are always in the same places, but you might have extra factors of stuff depending on what book you're reading. Okay, so
normalization factors, right?
Yeah, I think so, yeah.
Yeah. Okay.
So the generators have some interesting relationships. So if we multiply the xy by the yz, we get this matrix, which, it's pretty boring. Just have that one up there. And if we reverse the multiplication, we get another pretty boring matrix, just with a 1 down here. But what's interesting is if we take the commutator, so basically this difference times this difference, or minus this this product minus this product. So we take this matrix minus this matrix, we get the ZX generator. So the commutator of two generators gives another generator. So we get all these relations. And an easy way to remember is like, you notice how there's x, y, and y, z. I can cancel out the y's, and then I think just flip the order of x and z, and then I get the resulting generator. And I think here you can like
to the quaternions, the ij and k, I believe.
I'm trying to think about that. Does it?
Yeah.
Flip the order, you get a negative sign.
I see.
And you get the third one always. Yeah.
It is true because
yeah.
SU2 and SO3 they will have the same Lie algebra. So.
Yeah.
Yeah. Okay. Interesting. Yeah. So So basically, I don't know if I wrote this anywhere. Basically, the rotation matrices themselves, like this, and then this, these are called the Lie group, SO3 in capital letters, because they do 3D rotations. SO stands for special orthogonal. Transpose is the inverse, and then special means the determinant is +1. I think like if it's just orthogonal, you can get rotations and reflections, like if you don't have this determinant constraint. But if you require the determinant to be 1, it's just rotations. And then these generators that generate the Lie group, this is called the Lie algebra, and it's lowercase SO3. So basically, anytime we have a Lie group that's like a matrix group, continuous matrix group, there's going to be a set of matrices that exponentiate to it, and those are the Lie algebra. And they have different, because like this is a 3-dimensional, so there's 3 generators, but you can have like different dimensions, and you'll have like all these commutation relations depending on the number of dimensions. So one question to ask is, given these generators, are there other matrices that also satisfy these generator commutation relations? So, I forget where I was going with this slide. So, but basically, when a matrix is orthogonal, we have the inverse is the transpose. So if we have R times its transpose equals the identity. Now, if I were to say R is this exponentiated matrix here, so like X is the generator, and then this would be just that matrix transposed, and then 0 generates the identity. So basically, I've written R transpose, and I as exponentials, where e to the 0 just gives the identity. It turns out that because if you remember, like, the exponential of a matrix is just like, just an infinite series. And if I transpose this, it's the same thing as transposing each individual matrix in this term. So I can kind of put the transpose just on the actual X, the generator itself. And then I have a product of exponentials, so I can just add their exponents.
Yeah.
So you'll notice we have.
Can I
go
add?
ahead.
I just want to say that you should be really careful here, because you need to use here the Baker-Campbell-Hausdorff formula for getting those matrices together.
I might be oversimplifying a little, so I might be like hand
other
waving.
ways to express the same thing. You can take it like mod S and P squared. I think that's how it's done in the book that you referenced before.
Yeah, so if you have those matrices like X and X transposed multiplied by T, and all of their commutators will be equal to 0, then you can do use your formula. And I think that for simple groups like SO3, it's kind of true. So you have the commutator relations for those 0, but I don't remember exactly.
So this step maybe comes with a warning sign, because like I'm kind of making a simplifying assumption, but I'm not going to worry too much about that. Yeah, maybe this slide should not be taken literally, but like it's kind of like an argument, like a half proof, just to like get us going. So if I look at the exponents, I basically get x plus the transpose equals 0, or x transpose equals minus x. So what this is saying is that, yeah, when we have R being a member of a rotation reflection group, its generator will be antisymmetric. So we might try and find other antisymmetric matrices that satisfy these commutation relations. And then, yeah, so I think with orthogonal, which is rotations and reflections, the determinant is plus or minus 1. You can like make the argument this just becomes the determinant of R squared. But like the plus 1 is like rotations only. And then the plus or minus 1 is rotations and reflections. So I think we only want to focus, which is like SO instead of just O for the group. So there might be some other antisymmetric matrices that satisfy this relationship. And I think, so this is like the sigma matrices. When you multiply 2, you get the third one times I. So that's a nice fact to know. And I think if you anti-commute 2 sigma matrices, you almost get the third one, but you get a factor of 2 in front. It's like 2i. So basically what you can do is you can say, well, if I add this 1/2 I and I'm going to add negative 1/2 I here, I get like, I'm honestly not sure if I got the signs right, but basically the sigma matrices almost satisfy this, but you have to put in some 1/2s, some i's, and maybe some minuses in some places, and you can satisfy this set of relationships. So I think I have that clear on the next slide. Yeah, so these generators, which you can see here, they satisfy the same commutator relationship, but instead of being 3x3 real matrices, they're 2x2 complex matrices. And they generate these matrices, which are SU2. So we saw these when we were like rotating spinor states. If you remember like the flagpole from the first talk, we rotated the flag with SU2 matrices. And the Lie algebra is the lowercase SU2. So this is the Lie group SU2. This is the Lie algebra SU2. So yeah, so these are matrices from SU2. So basically, these are sort of like SU2 and SO3 have the same Lie algebra. So they're like kind of very deeply connected. And I think, I forget what I showed here. This is the, instead, SO13 basically is like the space-time rotations. So they include physical rotations and boosts. A boost is like a rotation between space and time. Yeah, I wrote that literally right there. So these are like the standard space rotations. So this is like X, Y. You can see like if we have like time X, Y, Z, this is like rotating X and Y. This is rotating Y and Z, and this is rotating X and Z. That's 3 rotations. There's also 3 boosts. So this is like, again, T, X, Y, Z. This is a boost. This is like a Lorentz boost in the X direction. It's a hyperbolic rotation instead of like a circular rotation. And then this is a boost in the Y direction. That's a boost in the Z direction. So SO13 has 6 it's 6-dimensional. SO3 had like 3 matrices, but SO13 has like 6. You can think of it as like all possible pairs of axes. So X, Y, Z, X, Y, Z is 3. Here we have those 3. But we also have time, so that gives us 3 more pairs. So that's why it's 60. And these have generators of their own. So I've showed you the cos and sine Taylor series. There's also a cos H and sine H Taylor series. They're actually easier to remember. Instead of swapping the plus and minus signs, cos H and sine H just always use plus signs, so it's actually easier to remember them.
I think it's also worth noting that SO13 isn't compact, so representation stuff can get a little funky. Same rules don't always apply.
I'm not really a topology expert, but when I think of compact, I think of like you can like put it in a box. So like a circle you can put inside a box, but a hyperbola kind of goes on forever, so you can't really like put it in a box. Your box just is never going to fit around it. So SO13 is not compact. I don't really know what that implies because I'm not. There are people in this call who are better at representation theory than me, but that's what compact kind of means. So we have these 3 rotations and 3 boosts. They end up getting their own generators. I called them J for the physical rotations and then K for the space-time. And again, different textbooks might have like the I's or like a minus I thrown in. You'll notice that the J's have a minus and a plus 1, whereas the K's only have plus 1s. And they have a whole bunch of commutation relations. So I tried writing it out this way. It's a bit confusing this way. You can kind of do what you did before and like cancel out the Y's and swap the order. So you'll notice that the commutation of 2 physical rotations is another physical rotation. When we commute 2 boosts, the T's cancel and we get a physical rotation. So this is kind of interesting. The rotations form like a subgroup or a sub-algebra, I guess. But 2 boosts don't commute to a boost. They commute to a physical rotation. And then a boost and a rotation commute to a boost. So the way it's written here is a bit confusing. As I said, you can kind of cancel like whatever shows up twice. But you can get like signs that pop up that are hard to remember. Another way of writing it is we can write YZ as J1, ZX as J2, XY as J3. And now the trick is to get K1, we use the 2 variables that we didn't use in J1. So since we used up Y and Z, then for K1 we use X and T. And then since we use Z and X, for J2, for K2 we use T and Y. And then for J3, since we used X and Y, we use T and Z. So this is like an alternative notation for these generators. Yeah, so basically whatever, you don't necessarily have to, like some people might call this like J3, like they might disagree on the number, but whatever numbering system you give, the rule is that the J and the K with the same number can't have any shared indices. That's like kind of the rule. And basically if we write them like this, we can do a change of basis in the generator space. So we're going to say like A1 equals J1 plus I K1. And that's like 1, 2, 3. N can be 1, 2, 3. And then B, it's the same thing, except we do a minus I. And then we do that for like 1, 2, 3. And if we do that, we get new commutation relations where the A's commute to themselves and the B's commute to themselves, and then they don't commute with each other. So these kind of look like, if you remember SU2, we kind of got like a factor of I with like the sigmas. I I might be mixing the physics notation and like the math notation,
like H,
but basically
x bar and x plus, the raising, lowering, and Hamiltonian. Right?
Maybe again, I'm kind of new to this, so I don't know what these are.
Yeah. Fair.
But yeah, all I really know is that when we have SO13, this algebra is 6-dimensional. We can kind of break it up into two 3D algebras using this change of basis. So the SO13 algebra is kind of like 2 copies of SU2, if we do this change of basis in the right way. And maybe those are like raising and lowering operators, but I don't actually know.
Yeah, there is a subtle thing here actually. So it is described actually in Physics from Symmetry book by Jacob. And he says that after the complexification here, in reality, we are losing the SU2 group, or like SU2 the algebra here. So in reality, we'll have like the SL2C group.
Oh, okay.
2C.
That's
Yeah.
Sorry
It's
about
SL2C.
that. My
Well,
bad.
I think it's the whole thing is just SL2C, I believe.
Oh, the whole thing? Okay.
I think so.
I thought there was a way you could like break it up.
Yeah, I already opened the book just to take a glance at the notes there.
Well, because like just as like SU2 kind of double covers SO3, I think SL2C double covers SO13.
Yeah, I think that's true. I also know that the complexified Lie algebra of SU2 is SL2C. If you complexify the Lie algebra, you get SL2, which are these matrices.
Okay.
Yeah.
Okay. So I might have maybe skipped some details here, but
something, it may still be right, at least the direct sum, but I'm not sure on the isomorphism.
Okay.
I think there's a factor of I that should be in one of them that's not visible.
Yeah, this is like my 3rd week doing this, and I just didn't have the patience to like make sure all of my I's and my signs were right. So
yes,
I'm trying to get the concepts.
The first variant was right.
I'm not having a go at you. You're doing fine.
Okay.
Yeah. I just wanted to say that the first variant was right, like SL2C direct sum with SL2C. So it's the right variant.
This is 2 copies of SL2C? That seems wrong to me.
It is 2 copies, yeah. Because, like in Physics from Symmetry, he has a note that, like, we consider the complexification of Lie algebra SU2, which is also called SL2C. So, complexification of Lie algebra SU2 called SL2C. Therefore, you'll have 2 copies here. And also, one more small note here, that this exact direct sum will be like a Lie group. So in terms of Lie algebra, that's okay, yeah. So it is true, it is Lie algebra of SO13, but it will be contained in only one part of SO13. Because like SO13 consists of 4 parts. It seems to me.
Yeah, I might have to go back and check this. Yeah. But I might move forward. Yeah, I might have to go back and double check this to get it right. But there's a way you can basically do sort of the same thing and get generators for the spacetime group. Okay, and that's actually it for this part. So I guess, the main thing is like when you have like a group matrix, like a continuous group, you can write it as the exponential of a generator, or a physicist might write it as like a slightly different matrix with an I factor. And the way you get that is you just take the derivative, and then you get an m in front, and then if you evaluate at 0, then you get M. So basically, if you take the derivative of your matrix and evaluate at 0, you can get the generator. That's sort of the main idea. And then, yeah, so you can do this for like the 3D rotation group, and you can also do it for the space-time. I guess that's called the Lorentz group. And then you get like so the rotations make up the Lie group, and then the generators make up the Lie algebra. And you can find different groups with the same Lie algebra. So like SU2 has the same Lie algebra as SO3, and then SL I think it's 2C has the same Lie algebra as SO13.
Yeah. I just wanted to ask you, will you talk about geometric interpretation today?
Like the 3-sphere and the sort of thing like that?
Yeah.
I'm going to talk about that a little. I think that's part 6. Part 6 is actually pretty short. I think I ran out of steam on this section a little bit, but yeah, I talk about that a little bit.
Yeah, okay. I just wanted
heavy.
to...
You did a good job for what I saw.
That's totally true. Yeah, and he's Chris actually is doing that job for 3 weeks, so we have like previous episodes on YouTube. Yeah.
Yeah.
What a mad
This
lad.
is like, well, I've been learning this for like the past 6 months, so I try to like get it all out so that other people.
Yeah.
I don't know if I'm actually helping people or just confusing them. I hope I'm helping a little bit. Anyway, do we have any more questions before we move on?
Yeah, I just wanted to say one small note about that. If you take a look at those groups as geometric objects, you will understand that the Lie algebra is kind of, how it's called, it's a tangent space, actually, to the manifold. So you have object, you have like a tangent plane. That's like basic intuition there. And you will see that SO3 is actually the part of SU2 in terms of topology or geometry. So SU2 is kind of the best one, the best group with the fixed Lie algebra, because it is the connected one, like it has connected manifold.
Well, it's simply connected.
Simply connected. Yeah.
Yeah, I'm going to talk about simply connected later. But basically, if you think of it's hard to imagine 3D rotations a little bit. I'll talk about visualizing it later, but you can imagine an XY, a YZ, and a ZX direction. You have 3 separate angles. And then at the middle, you have the identity. That's like the 0, where all the angles are 0. And when you take this derivative at the identity along one of the parameter curves, you're basically getting a tangent vector that lives in the tangent plane. So this might be GXY or something is this basis vector here. It's a matrix, but it's kind of it's a basis vector in the Lie algebra. So the Lie algebra is like a tangent plane at the identity. It's not like a literal 2D plane. It's like a 3D tangent space that sits at the identity in the 3D group manifold. But yeah, I'm going to talk about visualizing it in the next section. So I wanted to talk about spin groups and how they're the double cover of SON. So SU2, I said, was the double cover of SO3. SU2 is also called spin 3. So the spin N double covers SON. It applies in any dimension. If we go back to Clifford algebras, so remember, in Clifford algebras, things will, a vector will square to plus or minus 1, and then we need to anti-commute everything. So, for example, sigma x, sigma y, sigma z, all square to plus 1, and then they anti-commute. So if we switch their order, then we get a minus sign, provided that they're not the same. So I just wanted to mention a couple things about Clifford algebras, like operations. The first one is called reversion, and it just reverses the order of the elements. Some people write it with a T, some people write it with a wave. But basically, if you have like sigma x, sigma y, and you do the reversion, that just like switches their order. Or in this case, if I have ABC, it reverses to CBA. And to some extent, this is kind of like a matrix transpose, because like the transpose of a product reverses their order. I think if you because sigma matrices are Hermitian, right? So they equal their own Hermitian conjugate. I think if you Hermitian x, y, or if you Hermitian conjugate them, you switch the order, but that just, since they're equal to their own daggers, you basically just switch the order. So the equivalent of reversion in a Clifford algebra, if we're dealing with matrices, it's kind of like a dagger operation. It's kind of like a transpose conjugate. And then another thing you can do is called parity inversion. Sometimes it's written with an alpha, sometimes it's written with a bar. The notation for this is really confusing, but the idea isn't that hard. Basically, you just send an element to its negative. So odd elements, if it's like 1 or 3 or 5 or 7, will get a And then there's like the doing them both at the same time is called like the main automorphism. It's written with a star. Again, the notation is really confusing because like star means different things. It can mean like the complex conjugate. Different books use different symbols, but like this is just some things you can do in a Clifford algebra. So when we have this is like when I talk about a metric with a signature that has P and Q, it basically just means when we take the squared length of a vector V, the first P components squared up get a plus sign in front, and then the last Q components get minus signs in front. So like in relativity, we would say that this is a 1-3 signature because we have 1 plus and then 3 minuses. So you can generalize that to P and Q. So when we have a special orthogonal group PQ, that just means we do a rotation that doesn't change the metric value. So like SO, this is 3D rotations. It doesn't change like the dot product in 3D space. This would be rotations in spacetime or Lorentz transformations, and it doesn't change like the spacetime dot product. So that's what SOPQ is. It doesn't change the dot product for like a metric with like P plus signs and Q minus signs. And then like the orthogonal group, the special orthogonal does rotations, but the orthogonal group allows for rotations and reflections. So I think this is like determinant +1. This is determinant plus or minus 1. So it can do reflections as well. Reflections don't change the length, but it like reverses reverses whatever.
It's orientation preserving versus allowing it to flip. So it's not necessarily reflections, but it's something that can like.
Well, I guess it could be like a rotation and reflection at the same time. Like if I have this flag.
But any rotation is a composition of 2 reflections. So basically, we'll have like maybe a chain of reflections. But anyway, I think that you will get a reflection with orientation change in there.
Right. Yeah. So basically the group SOPQ has a double cover called spin PQ. So when I say double cover, it means there's two elements in spin for every one in SO. So here's how you get spin PQ. You take the unit length and even grade members of the Clifford algebra, CLPQ. So like if this was CL30, the even grades would be the scalar and the bivectors. So we ignore the vector and the trivectors because they're not even grade. So we start with those, and we take only the unit length ones. So I think like cosine 1 plus sigma x, sigma y sine, that will square to 1. So that's an example of like a unit length one because it squares to 1. So basically, so basically the unit length even grade elements of CLPQ.
Yeah, I just wanted to say that in the expression at the top, you can have like any bivector combination near this sign. So
so like
it's kind of the same when you have a Varsor representation for the quaternion. You'll have like cosine theta plus Varsor by sine theta. So it kind of is the isomorphic representation actually.
Yeah, so spin 3 is literally the quaternions. Like quaternions of unit length,
the pure
do rotations.
Pure quaternions.
Yeah, so spin 3 and quaternions are the same thing. And if you know quaternions, you know that you do a double-sided transformation to do a rotation, right? So
Tim actually gives you like a how to say that, a good tip that it is a pure quaternion, so they are versors or something. I don't remember the correct name. I think it's called versor. So it's quaternions of the unit lengths.
Yeah, so if you want to call them versors, yeah. So, but basically, when you use the unit length quaternions or the versors, you rotate using a double-sided transformation. So, I think, is it the inverse? I think if they're unit length, then the inverse is the conjugate.
I think it just has to commute with multiplication by j, the quaternion j, something like that.
Okay.
I'll get it in front of me.
Okay, but basically in a Clifford algebra, if we have a vector, so like maybe like sigma x, we can rotate it by doing a double-sided transformation with even B is like one of these. It's like a unit length even grade member. You can think of it as a quaternion if you want. But the reason it's a double cover is because B and negative B do the exact same thing. So like the negative signs here just cancel. So because it's a double-sided transformation, the sign of B doesn't matter. So that's why there's two group elements in spin that give you the exact same rotation because it's a double-sided transformation. And then also, this is kind of silly, but the orthogonal group has a double cover. Instead of being called spin, it's called pin. The reason it's called pin is that since SO, I'm not making this up, SO has a double cover called spin, you just get rid of the S's, so O has a double cover called pin. It's literally in textbooks and Wikipedia articles, it's called pin. So basically, again, there's two elements in pin for every one in the orthogonal group. And instead of unit length even elements, it's just unit length. So you can have odd elements as well. And they do reflections. Yeah, the even elements do the rotations, and then the odd, I guess I'll call them like reversions because they can be reflections plus reflections and rotations at the same time. I think that's called a reversion. But
actually, it seems to me that reversion is actually a scaling plus reflection. Or scaling plus rotation. I don't remember. So it's not the right word here, I think.
So, but basically, instead of just doing rotations, you can do rotations and reflections. So, the even grade things will rotate, but the odd grade things will do both. And you apply it like this with the minus sign in front. So if you do it twice, then this minus sign goes away. But if you only do one, you need the minus sign in there. That's what you need to do a reflection. And I think I talked about that in like the first video, why that minus sign needs to be there. Basically, if we want to reflect sigma z, in like the xy plane, we apply sigma z on both sides. That squares to 1, and then the minus sign will give us a minus sigma z. So that's why the minus sign needs to be there. It sends sigma z to minus sigma z, which is like a reflection. So the orthogonal group has an double cover called pin. The special orthogonal group has a double cover called spin. And just as the special orthogonal group is a subset of the orthogonal group, spin is a subset or a subgroup of pin. And both pin and spin live inside the Clifford algebra. They're basically like the unit length elements of the Clifford algebra. So remember CL, I think 1-3, the even grade unit length are literally just quaternions, which I think are called H for Hamilton. So spin groups are like
CL1-2. I don't know if it's 1-3.
So that's an interesting point.
It's a notation thing.
CL1-2. Let me think about this.
Because CL the real the first real.
Sorry. Yeah.
The second one is
you're right.
C, and the third one is H. I guess it could be a notation thing, because with mixed metric it can be weird. I don't know.
Yeah, so I think actually you're right. I should have written it as CL30. Yeah, you could maybe do it with 2 minus 2-1 as well. I'm not sure.
I think you might be right. Mixed metric is weird. I don't know about it.
Yeah. So sorry, I was confusing space and space-time. I'm talking about space. Quaternions only rotate in space. But basically, spin groups are a generalization of the quaternions. The quaternions do rotations in 3D. Spin PQ does a rotation in your PQ space. So spin 1-3 would be like the equivalent of quaternions, but for space-time. They do the rotations in space-time. Rotations being like actual physical rotations or boosts, because a boost is a hyperbolic rotation in space-time. And like, you could have your spin like, I don't know, 23-9. Like, this is a procedure to come up with this spin group for literally anything. You would never use it for 23-9 because you would never want to do that, but you could. It exists, and you can build it. It's just the even grade unit length elements of the Clifford algebra.
Yeah, I just wanted to make a small fix here on the previous. Yeah, that like instead of just quaternions, you will have once again like unit length quaternions only, right? Or the even grade.
Unit length. Yeah, sorry.
And quaternions will be actually all even grade elements, and therefore they are spinors, right? So spinors are quaternions.
If you use the Hestenes definition, like, do you remember how I talked about how there was the minimal ideal? Like, Hestenes would say that's a spinor, like 5. But if you want the minimal ideal definition, you would need to project it down. But, this is the Hestenes spinor. This is like the ideal spinor.
I think
you have to project it.
I think these things also have to be, invertible in the right way, like the orthogonal and special orthogonal groups are. They have to be like their own. I think under the main involution, they have to be their own inverses, something like that. In the same way that
I'm not sure.
Its transpose is its own inverse. There's another requirement missing, but I don't remember what it is off the top of my head.
Okay, yeah, sorry, I might have missed something there, but
it may come for free with the other ones. I'm not sure if they imply it. I may just be misremembering, in which case I apologize. But I think there's another one.
Yeah, fair. Yeah, like in lower dimensions, things can get like simpler, but in the higher dimensions, you might need like extra.
Especially
so
with when it's not mixed metric, these things are all compact groups and they're much easier to deal with. When it's mixed, it cannot be compact. In which case, some of these things that I'm thinking of may not apply, which I don't know. So with spacetime, I'm not sure.
Okay,
so
and again,
you may be right.
I haven't studied, like, again, I barely know what compactness means, so I don't have much to say there.
Anyway, we have a paper, like, we are not the authors of the paper, but we have seen a paper where authors have the exact same definitions. So probably, if we believe them, those should be right, actually.
Yeah,
Okay.
Cool.
So this is just like, I think I said last time, Clifford algebras are like diamond shaped. So like there's one, this is CL, this is the space-time one, so 1, 3. So we have one scalar, 4 vectors, 6 bivectors, 4 trivectors, and 1 pseudoscalar or quad vector. So the even ones are like these, and I guess this. So the even is like 8 of them, and then the odd would be the other 8. So like I think a rotation, like a boost, I might be misremembering, but I think it would look something like this, where like Dirac 0 is like time. So I think this would be the equivalent of like a Lorentz transformation or a boost in the 1 direction, or like 1 is like x in space-time, and 0 is t. So that's sort of what a boost might look like in the spin 1-3 group. That this is a unit length.
Yeah, so it seems that hyperbolic functions comes out from the mixing the positive Clifford algebra basis elements with negative ones.
Yeah, so like this thing here, I think squares to, I'm trying to think, I'm going to have to calculate it. So 0, 1, 0, 1, and then we flip the order. And then these go to -1.
It'll square to 1, I think.
Yeah, so when you have time and space, that squares to +1. But when you have space and space, that squares to -1. So basically, when you have space-time, that's why you use cosh and sinh, because of this squares to +1. But when you do space and space, you use cos and sine, because the thing will square to, like I don't know, 2, 3 will square to -1 instead. Yeah, so like these ones give you the boosts, because they square to +1, and then these 3 give you rotations, because they square to -1. And like if you think of like I in the complex plane, I also squares to -1, which is why it kind of gives you rotations. That's like the complex numbers I said before are just like CL10. They're like the simplest Clifford algebra. And I think, fun fact, CL10, that gives you like a plane where you just do Lorentz transformations, like the thing that squares to +1. I think I called it P. That'll give you like just Lorentz transformations in the plane for that vector space.
I think CL the first one is just the real, like over the reals. The first one's the reals. The second one is the complex numbers. The third one's cyclotone. So you just get everything back that we're familiar with in the low case with no mixed metric.
I forget what this slide is about, so I'm just going to read it. So, let's make a bivector out of orthogonal vectors. So, like, if 2 vectors are orthogonal, because normally the Clifford product, you have a dot product and a wedge product, but I guess if they're orthogonal, the dot product just goes to 0, so the wedge product is the Clifford product. What happens if we conjugate A and B by the unit vector? Okay, I think I remember this. So, let's say that, like, if U is a unit, if these U's are all unit vectors, then multiplying them all together gives you another unit element. So I'll show you what that means. So I've conjugated A here, and then I can conjugate B. Now what happens if I conjugate A and then I conjugate B? So you can see I've reversed the order here because I did a reversion. And basically the U's cancel to 1, and then the U2's cancel to 1, and then the U3's cancel to 1 because they're all unit vectors. And I end up with just like conjugating AB. So I don't know why I put this slide in here, honestly. But I guess I wanted to say that you can, when you like transform, like if I reflect A and then I reflect B, which is I guess just like the same thing, then I can also reflect like the bivector AB, and I don't know why I wanted to say that.
Yeah, probably you just wanted to say that you can reflect and rotate by using that conjugation formula the higher order
so like,
vectors, like multivectors, like cubes.
Yeah, so
higher order ones.
Yeah, you can. I guess instead of just thinking of spin as applying to vectors, it can apply to like bivectors. It could apply to like trivectors. So you can pin and spin all of these things. It doesn't just apply to vectors. I guess that's why I put it in.
The biggest thing about that, which is kind of profound, is that the Clifford algebra is isomorphic to the exterior algebra. Given, well, if you have an inner product, which in this case we have the 1-3 spacetime metric thingamajig, if you have the tensor algebra over some vector space, and you quotient out some, this is a technical definition, you quotient out some ideal generated by a certain squaring property in to do with the metric, then you get the exterior algebra, which is the stuff to do with the wedge products. And it turns out that they're isomorphic. The Clifford algebras are actually the same as the exterior algebras over the vector space. Not the same.
Yeah.
But there's a isomorphism of algebras.
Yeah, but there should be some kind of the restriction on the metric there. I think I don't remember the exact one. It's not. It is on the Wikipedia page for the Clifford algebra, but I don't remember
I think as long as the underlying field isn't characteristic 0, it should be well defined. Well, I think the metric also has to be non-singular or something. But for space-time, that's a given.
I mean, like the more common English way of saying it is that, like with Clifford algebras, you have a dot product and a wedge product. So, like, the way I've said it before is that the Clifford algebra is like an upgraded version of your exterior algebra, where you also have a dot product. And I guess if you forget about the dot product, you're just left with the exterior algebra, which is like the wedge product.
I'm pretty sure that they're actually isomorphic as algebras. Under most conditions, I think there are extreme cases where it doesn't happen, but under most cases, they're actually the same thing. You can find a bijection between them that preserves all of the algebra-ness about them.
Okay, I guess I can't comment on that, but they're definitely similar, possibly like isomorphic, like you said.
Yeah, so it's a tricky question. I opened the Wikipedia page, and it says that if our matrix equals to 0, then it is true. And for non-zero matrix, there exists a canonical isomorphism between exterior algebra and Clifford algebra whenever the ground field K doesn't have characteristic 2.
Yes.
I don't remember.
That's the most pathological case. It's basically because everything is its own additive inverse. So the ideal that's generated, the U quotient out of the tensor algebra, becomes trivial because you're declaring that two things are equal when you subtract them. But you kind of really it's because you can't tell the difference between a quadratic form and an inner product. The different
so characteristic
they're not the same thing in character.
Characteristic it means that if you square any element you will have the 0 and that's it. Yeah.
Yes. Yeah. Yeah, and so in with reals and complex numbers, the characteristic is 0, so none of that matters. It really just means that there's no number that, take anything to any power and it doesn't go to 0.
Yeah, so that kind of means that we can think about the Clifford algebra in terms of geometry.
Yeah. In terms of alternating tensors, which are probably more familiar to most geometers. I'll try to find the page in my textbook and put a picture in chat so I can just keep talking. I don't want to take it.
Okay, so I think we're almost at the end of part 6. Basically, I think I've said this before. There's 2. It's a double cover, so there's 2. You could say either SU2 or spin 3. They're the same thing for every SO3 matrix. So I think this is cos of theta over 2 plus. I think this is I want to say it's sigma y, sigma z, sine. No, there's no I here. And then just sine. So if you 1 is just the identity matrix, which is why cos is on the diagonal. And then you can either plus or minus the sigma y, sigma z term, and you'll get either this or the minus version of that. There's two of those matrices for this, and same thing with I'm guessing this is xz and xy, and the reason is if we transform double-sided a vector with the negative version of r, then the negatives just cancel, and that's the same thing as transforming with the positive version of r. So because it's a double-sided transformation, the plus and minus do the same thing.
Yeah.
Now, I wanted to visualize this.
Sorry, Chris. Can I add a bit of information here?
Sure,
I just wanted to say that those capital R's, they are rotations, right? Or
they could be. I don't know why I used R, but they're spin 3 members. So SU2. So I guess they're rotations. Yeah. I don't know. I think I might have done some copy pasting.
Probably I should skip now. Yeah, I need to think more about it. Okay.
Yeah. So the last thing I wanted to say.
Taking the Lie derivative of a matrix from the group, just they correspond to the Lie derivative of one of the rotation matrices. In the base group, something like that. Anyway. So he's right. Yeah.
Yeah, I haven't studied the Lie derivative. But the last thing I wanted to say is you might hear the phrase simply connected and not simply connected. So basically, a simply connected space basically has no holes. That's kind of the English way of saying it is simply connected. And then a not simply connected space has holes. So the way they talk about this in math is if you have a loop in your space, you can sort of pull on both sides and close the loop up to a point. Whereas in my not simply connected space, I kind of get stuck around the holes and I can't really close the loop up by pulling on both sides. So that's sort of an intuitive definition. So a sphere is simply connected. So we have the equator. If that's a string and you start pulling on it, you can sort of contract the loop to a point. And I think this applies for any n-dimensional sphere. So this is the 2 sphere, but it would apply for the 3 sphere and so on. So a torus is not simply connected. So this is an example of a loop that you can't pull on because there's the hole, and the hole stops you from contracting loops to a point, basically. The reason I bring this up is because topologically SU2 is the 3 sphere, and by that I mean it's living in 4-dimensional space with 4 variables, but with the restriction that this equation equals 1. So this is a metaphorical picture. I can't really draw a 3 sphere, so I just drew a 2 sphere. But basically, a member of spin you can think of it as living on the surface of a 3 sphere. All the points on the sphere are members of SU2 or spin 3. Now SO3 is what we get when we identify opposite points to be the same. So remember how there's two spin 3 points for every SO3 point, right? So if basically this point over here and this point over here, these give like the same rotation. Like the plus version, I don't know if you want to call this B, this would be like negative B or negative R. They give the same rotation. But SO3 is basically what we get when we consider opposite points to be the same. So SO3 is like a projected version of SU2 where we're saying, hey, this is the same. Like we literally can't tell the difference between these 2 points.
And therefore...
So you might say like V and negative V are equivalent.
Yeah, and it's kind of the same way in which you are forming the projective spaces. For example, in 2 dimensions, if you draw a circle, to build a projective space, you need to make the same identification. Like, you need to glue the bottom of the circle to the top. And in this case, it will be the same process, but in 4 dimensions, and therefore you will have half of a sphere. So you kind of wrap it up, like pop it, pop it inside or something.
Yeah, you can sort of think of it as half a sphere, where if you go to one side, you just magically teleport to the other side because opposite points are considered the same.
Yeah, and if you think about
but yeah.
SO3 as 3-dimensional manifold, you will discover that it is actually a 3-dimensional ball. So it's not a sphere, it is a ball, but a ball with a property that you can teleport from its surface to the diametrical point because of the identification of that great diameter circle in 4 dimensions. So you can teleport from...
Yeah, SO3 is, I think it's actually diffeomorphic to RP3 or RP2. So it is actually like as a manifold, it's the same as one of the real projective spaces. I think it's RP3. It's like a sphere across a circle or something.
So if you take this like half sphere here and you flatten it out to a disk, you end up getting like a disk where if you go to one point on the edge, you just teleport at the other side. So that's why this like 2-sphere with the opposite sides identified is like a 2-dimensional disk.
Yeah.
With this like warping property. So you could think of SO3 as like it's a 3-sphere, and then you chop off half and then flatten the rest into, I guess, into like a actual ball. Like I don't know, where you can go anywhere in the middle, but opposite sides teleport you around. It's kind of hard to imagine. But the reason I bring up connectedness is that on an N sphere like SU2, you can always contract the loop to a point. So this is connected. But with SO3, I tried to draw a loop here. Because opposite sides are identified, if you try and move the loop away in one direction, the opposite side kind of like runs away from you. So you can't ever like contract the loop to nothing. So this is not simply connected, because like if I try and run away here, the other end is going to run away from me, so I can't ever close it to a point, basically. So that's why spin is always connected, but SO I think is generally not connected. Or sorry, I should say simply connected, because simply connected and connected are not the same thing. So basically the spin spaces are almost simpler because they're simply connected, almost kind of. But the SO spaces have like a hole that you can't like get around. It's really hard to visualize it in higher dimensions, but it's kind of like this, where you can't contract a loop because the opposite side runs away.
Yeah, but there is a tricky thing here that like you could have only 2 kind of paths in the SO3 manifold, and the one is if you go from the like south pole to the north pole, it will be isomorphic to like any other like similar string in the ball. but you can have one more kind of a pass if you go back. And that going back corresponds to like 720 degrees rotation or something. So you can contract that loop.
Yeah, so that's kind of like why spinners, like when you bring them around once, because like spinners live in like in SU2 in spin 3, when you go around half a rotation, you get a minus sign, but that's like a full rotation here because it can't tell the difference between these 2 points, so it thinks it's back where it started. So in spin, it's like you get a negative sign, but for SO3, it thinks it's back where it started. That's why 2 rotations in spin is like one rotation in spin is like 2 rotations in SO. So that's sort of, when you first hear about spinners, you hear like, oh yeah, when you go around once, you get a negative sign. This is like the more mathematically complicated way of saying that, is that because one is the double cover of the other, a half rotation in one corresponds to a full rotation in the other. And this kind of goes back to the beginning, how I was saying, like in physical space, like with the block sphere, up and down states are like literally up and down, but in like the spinner space, up and down are at right angles because their inner product is 0. So when you go around half here to negative up, physical space treats up and negative up as the same, because like phase differences don't matter.
Just one thing that I'm not sure if it is or isn't the case. It might be. I'm not sure that spin PQ is always simply connected. Like when the metric is mixed, I think things can get weird.
Okay, so if I throw a C in here, is that then true?
Yeah, I think you need to put a plus, like spin plus PQ, and it will be true.
Right, okay. Because like in Lorentz transformations, with like Lorentz transformations, there's like 2 hyperbolas, right? So you have to choose like the future pointing ones only.
Yeah, it's like orthochronous or something.
Yeah. They use like a really weird ortho. Like you can't do time reversals basically.
Yeah.
Chronus.
So we have like one more.
I don't know any of the physics, but that makes a lot more sense.
We just have more disconnected components for PQ groups. So if, for example, if you take O3, you'll have 2 of those, like rotations and reflections, like SO3 and the other one, where identity is not included. And if you take O13, like the orthogonal group for the Lorentzian spacetime, then you will have 4 of those. And you will take only proper orthochronous, those SO plus 1,3 group, and we'll work with it, and you will get all of the other parts just by using parity transformations and time reversals, I think.
Right.
Yeah, so proper means you don't reverse space, and orthochronous means you don't reverse time, basically. So that's cool. The S here means you don't reverse space, and I guess the plus means you don't reverse time, I think. Anyway, that's part 6. There is another part. If people want to hang on for another half hour, I can try and get through it.
Hey, you're doing really well. That's great.
How are people feeling? Do we want to break for this week, or do we want to power through for another half hour?
Yeah, I'm ready.
You're ready? Okay. So this is the last section. It's called spin half representations. So this is getting into, I guess, representation theory. And I admit I did a lot of copy pasting from Wikipedia here because I was just running out of like energy to actually write it all out. So basically, a Lie algebra representation is a set of matrices that satisfy the Lie algebra's commutation relations. So we saw this generates SO3, if you remember. So this is the Lie algebra little SO3, and they need a representation satisfies these. So we've already seen two representations. We've seen kind of like the normal one. This is like the one that's like more obvious, provided you know how to do the trick. Like provided you know that like e to the theta g xy equals like the xy rotation. That part might not be super obvious, but this is like the most obvious representation of SO3 is like the 3x3 matrix. And then there's like the slightly less obvious SU2 also, or little SU2 also satisfies this. So I think this was 1/2 I guess this is sigma z. This is 1/2 I sigma x, and I think this is 1/2 I sigma y, maybe with a minus sign, I think, in front. I think you need a minus sign there to make it work. So these are 2x2 and 3x3 representations. And turns out you can get 4-dimensional, 5-dimensional, 6-dimensional representations. Now, I guess physicists kind of did this, and maybe math people sort of copied them, but when we have representations, you can either label them by dimensions, so like a 1x1 matrix, 2x2 matrix, that would be SU2, 3x3 matrix, that would be like SO3, 4x4 matrix. So that, you know, this is like obvious. 1 gives you 1x1, 2 gives you 2x2, 4, so on. But I guess because there's also another way called spin, where spin j, the dimension is 2j plus 1. So the spin 0 representation gives you a 1-dimensional representation of SU2. Spin 1/2 is a 2x2 representation. Spin 1 is a 3x3. Spin 1.5 is 4x4. Spin 2 is 5. So I was pretty confused when people were talking about like, oh, the spin 1/2 representation or the spin 1 representation. If you want the dimension, you just use 2j plus 1, where j is your spin. So this is a table that I found. I didn't understand this until I saw the table, but it's good to know.
Just something that isn't really the case with the SO stuff. These do correspond to like n by n matrices. All of that's fine, but they're not necessarily related to like SO, like the higher SO groups or anything. They're just
this is all SO, or I guess SU2.
They're all SU2 representations, just as different sized matrices. They're not. It's not necessarily to do with SO3. It is it happens to be in the case of 3, but it isn't always, and not in the same way. It's related.
Yes.
But,
so
it's just a technicality, just making sure that that's.
I think SO3 only goes in the odd ones. I think, and I think since SU2 is like all the integers, but SO3 is only the odd integers. I think. I think that's
like
true.
That.
So, okay, so let's say that we want to get an n-dimensional representation of SU2. So those are n by n matrices that would act on an n-dimensional vector space. So like this would be like n by n, and it would act on like n by 1 vectors. So the vector space would be n-dimensional. We could label the basis vectors just E1, E2, all the way to En. But another common way of labeling them is you start at -j, and then you work your way up to 0, and then you get up to +j. So like, for example, if we wanted a 5-dimensional space, we could write the 5 basis vectors as E -2, E -1, E0, E1, E2. Or if it was a 4-dimensional space, we could do that as, that would be spin 3/2, I think. So the basis vectors would be E -3/2, E -1/2, E +1/2, E plus 3/2. So this is kind of a weird labeling, but it just has to do with like, this is the dimension n, and then this is spin j. So you can label by dimension, or you can label by like the spin. Spin labeling is a bit weirder, but it's more common in physics.
That and J, then I think, is called. It's one of the quantum numbers in.
Yeah, I think it's the. I forget what it's called, but it's
one of them's a magnetic one.
Yeah.
And the other one's something else. I don't remember the name.
Yeah.
Something like that.
So instead of writing if we have E2, we could also write that as a ket vector, just like 2, like that. So these are just different ways of writing the same thing. So we could also use these notations. Just to be clear, this is not the 0 vector. That's just the label of the vector, so it's the 0th basis vector. That might be a bit confusing. So in quantum mechanics, it's common to use this notation for basis vectors. And this will be clear on the next slide, but M is the mth basis vector in the spin J representation. So that might sound really confusing. I'm going to lay it out here. So basically, in the one-dimensional representation, which is the spin 0, we have one basis vector, so that's that, 0, 0. It's the spin 0 representation. In the two-dimensional representation, which is spin 1/2, we have two basis vectors, so it's the spin 1/2 representation, and they're labeled -1/2, +1/2. So that's like E -1/2 and E +1/2 for our two-dimensional space. In the third dimension, that's spin 1, so we've labeled them all with 1. And then the basis vectors are like -1, 0, and 1, which we've written here. And then it just keeps going. So like the first entry labels the representation, which is like the dimension, and then the second label labels the basis vector, if that makes sense. So I still find this pretty confusing, but do people find this okay? Like, is the explanation of what the numbers mean fine? Like the first number is it's the spin number for that representation, or like it's related to the dimension with 2j + 1. And then the black number, the second one, is just the basis vector label, which goes from like j, -j, all the way to, I guess it doesn't necessarily have 0. And then it goes to +j.
Yeah, I just wanted to say that those indices here, maybe you can recall that we have seen those in the chapter, I think, yeah, it was chapter 22. And we have talked there about complete set of the commuting observables. So those indices come out from those sets. So you kind of, in mathematical terms, you have that complete set will contain, first of all, Casimir elements of the algebra and also the Cartan elements. And those two indices you see here are exactly corresponding indices for the corresponding Casimir and Cartan elements for those observables. So I don't know the real theory behind those like Casimir and Cartan things, but I have seen the whole procedure done or carried out in the physics from symmetry. So if you need more details, I suggest you take a look at the chapter 22 and physics from symmetry. A lot of details in there.
So another thing that I can say about that is that these kets, they do everything is right that they correspond to vectors, basis vectors, orthogonal ones. But it turns out that they're actually spherical harmonic function, very special one. And the indices correspond to like the degree of the polynomial, and the other one just corresponds to you end up with one of them, and then you generate all of the others through a process to do with eigenvalues and stuff. It's unimportant. But each one of these things corresponds to an orthogonal function. So when you're doing stuff to do with like quantum harmonic oscillators, you have like your spins in different directions. They correspond to spherical harmonic, which are like it's where the orbitals come from, like the orbital clouds. They come from these functions. They're like crazy trig functions.
They're like the Y.
YML.
Yeah, whatever.
There's a whole Legendre polynomial involved as well in the phase shift part of it.
The Legendre polynomials. I've got a thing, a reference, if anyone wants to
read more about how this sub is constructed, because it's really cool.
Yeah, so you can arrive at these from different places. Like you said, I'm not going to talk about the spherical harmonics at all. And I think the Casimir operator is like S squared, and I think the Cartan is like SZ. So when you said that these were quantum numbers, I think it's like the S squared and the SZ quantum numbers. I think.
Yeah, that's true.
Okay, so yeah, this is not going to be very quantum-y, it's more just pure math, but yeah, those are useful things to bring up.
Well, the reason that it comes up at all is that because the harmonic functions they correspond to all of the irreducible representations of SU2. And the reason that we have the kets is because they're like a very, very nice basis of those functions.
I don't know what that means yet, because I'm really, really rusty on spherical harmonics. I haven't looked at them in a while.
Me too. I just wanted to say that
it's just where it comes from.
Yeah, we have seen the spherical harmonics things in the Road to Reality book. It's chapter 22, subchapter 11, and anyway, it's kind of really mathematician's way to get into spinors or those spin representations, but like you don't need those. You can come up with those things like in a simpler way. I think like you don't need to understand that thing. But maybe understanding spherical harmonics can get you like maybe a better picture. I don't know. But it seems to me like a hard thing to get, like waves, those like harmonic oscillations of a sphere.
I don't know if you all talked about this yet. Have you all talked about the proper Lorentz group or SO31 or SL2C or something?
Yeah, we were talking about it earlier, yeah.
All right, because I remember a construction. Have you ever talked about the Casimir invariance and everything else, too?
Slava just brought up. I've heard of a Casimir before. I've never heard of a Cartan element.
It's
before.
the the elements that commute with all the members of the group. The Pauli-Lubansky pseudovector, that sort of thing.
Yep.
All right. Okay then.
So it's Casimir because like it commutes with all the other S's, I guess. Yeah. Okay, so I think I start copying from Wikipedia here. So, and this is the SU2 Lie algebra. I think I switched to the physics notation, which is why there's an I here, because I didn't have that before in my previous slides. But yeah, so this is our spin 1/2 representation of the Lie algebra. It's just like 1/2 I times the sigma matrices. And then this is the 3D representation. So there's multiple representations for each dimension. You can like do a transform to like change basis, and the matrices will look different, but they're like equivalent. So these are a little bit different than the ones I showed on the previous slide, but they're still a 3D representation of this Lie algebra. I think this is a 4D. Again, these are from this page. I just copy pasted from Wikipedia, and then I think they give a. This is actually 6D. I guess I forgot to change that, and that would be spin 5/2, I think, not spin 2. So I was going to quickly show how you get these. I think one thing to notice is that the J matrices are always diagonal. So the J matrices, the Z matrices are always really easy to get because they're diagonal.
Yeah, and it's actually
zero, right.
What?
Yeah, I think they're trace. I think all of them are trace zero actually.
Yeah, all of them always have trace zero.
Because they have to be or do they have to be anti-symmetric? Or is it symmetric? They have to be Hermitian, I guess.
Yes, they have to the conjugate thing. I don't remember.
They have to be skew Hermitian.
I just wanted to say that that's the characteristic of the Cartan element. So it should be diagonizable basically, and the number of Cartan elements we will have is the number of of the generators which could be diagonalized simultaneously. So, and we have like only jx, jy, and jz, and you can diagonalize only one of them in some fixed basis.
Yeah, and I was also going to bring up on a previous slide, I showed that they were like anti-Hermitian or anti-symmetric. That was the math convention, but in the physics convention, they're Hermitian or symmetric. So that might be good to know, because previous slides I said the opposite, where they should be like anti-Hermitian, but now they're Hermitian because I switched conventions. Yeah, so the Zs are easy because they're all diagonal. X and Y are a bit harder, but they're like off diagonal a little bit. Like they're just one diagonal, kind of like sandwiched. They sandwich the diagonal basically. And then this, so you can already know where the non-zero numbers are for all these matrices, just because they're either diagonal for Z or like sandwiching the diagonal for X and Y. The challenge is just figuring out what the numbers actually are. So this is more copy pasting from my notes, I think. Yeah, I think I already said this. I'm just like going over like the notation for like spin and the dimension and the basis vectors. So I think the first step is getting JZ. I guess I switched. Sorry, I'm doing lots of copy pasting from different sources, so I'm switching notations. But like the JZ, all you have to do is take whatever J is and go from plus J at the top all the way to minus J at the bottom. So you can see for spin 0, it's just a 1x1 matrix of 0. For spin 1/2, I have plus a half, minus a half, so that's like plus J all the way down to minus J. For spin 1, it's 1, 0, -1. Again, that's plus J down to minus J. Spin 1.5, it's 1.5, half, negative half, negative 1.5. And then for spin 2, it's 2, 1, 0, -1, -2. So the Z matrix is usually very, very easy to get. The reason it's like this is because of this eigenvalue equation. We basically use the convention that the SZ operator acting on the mth basis vector gives the eigenvalue m. So like if this was like spin up, we would usually get like, or no, well, yeah, I think you'd get like plus a half, because spin up is basically the plus 1/2 basis vector. And if it was spin down, then we would get minus a half, where like spin down is just the, negative a half, negative a half basis vector. So basically, because of these rules with the SZ operator, we just get a diagonal matrix, because all the diagonals are just the eigenvalues, which are the plus J all the way down to minus J. Those are all the eigenvalues. So I'm sorry if that was confusing, but the SZ is always a diagonal matrix, where the diagonals are the eigenvalues of the SZ matrix. Is that okay? Is that sort of clear?
Yep.
Yeah, okay. Now the next steps are a bit more confusing because they use the raising and lowering operators. So again, we know where the numbers are. We just need to figure out what the numbers actually are. Okay, so this is like the SU2 Lie algebra here. And then we define S plus and minus as Sx plus or minus I Sy. So these are the raising and lowering operators. And you can find out that they have this property when we commute them with Sz. So like Sz commuted with S plus just gives us S plus, and Sz commuted with S minus just gives us negative S minus. And you can sort of reason out that the S plus acting on a basis vector will give us the next basis vector up. So like S plus acting on M will give us M plus 1. Now I made this mistake a few weeks ago. I thought this was the end of the story, but there's actually a coefficient here, alpha. And the same thing is true with the lowering operator. It'll give you the one less, but there's another coefficient, beta, that belongs there. I guess I call them alpha plus and alpha minus in these notes, but yeah, if you want to like pause this video and look back, I don't want to go through all the algebra, but basically when you define the raising and lowering operators like this, you get these relations where you can sort of go to the next basis vector with some scaling coefficient using the raising and lowering. And again, I'm just pasting from Wikipedia, but these coefficients end up being this. This is like the alpha, and then this is like the beta for the lowering operator. I apologize if you haven't seen this before, but I just didn't really want to go through it. I'm just kind of giving you the basic steps for how to get it. But you can basically derive what alpha and beta are for these raising and lowering operators. So like the good thing is that when we operate on a basis vector, we can get the next basis vector with a scaling coefficient, and we know what the coefficient is. It's just this big ugly square root thing here. So I think, yeah, so I choose to do this for spin 1/2, so j equals 1/2, and I think you can show that the S plus literally just gives you +1 as the coefficient, as your alpha, and the S minus, I think does it also give you +1? I think it also gives you +1. So these, in the case of spin 1/2, they end up being just 1s, which is very easy. And you can get the matrix elements just by operating on the basis vectors. And you end up getting 0, 0, 1, 0, which, so the raising operator in the spin 1/2 representation looks like this. And then the lowering operator in the spin 1/2 representation looks like this. So I know that's like a lot of crazy math for matrices that look really, really simple. But this technique works in like any dimension. So if you have like the spin 17 representation, you can still follow this procedure.
So it seems you will get the same coefficients we have seen in the table Joe sent, like Clebsch-Gordon.
Yeah, they're the Clebsch-Gordon coefficients. Yeah, that's right. Which are also related to spherical harmonics, I think.
Yeah.
Are they like normalizing the spherical harmonics? I forget what they do. But basically, yeah, so we defined S plus and minus like this. So if we take S plus and add S minus, I think, yeah, then we just get Sx back, and we have to multiply by 1/2. So this is Sx. It's just like 1/2 of x plus and 1/2 of x minus, or S plus and S minus. And then we can also get Sy from the raising and lowering operators. We just have this negative 1/2 of minus I, and so we get this. So that's just the familiar representation we saw here. It's just like half the sigma matrices. But you can use that same procedure. You can get J plus and minus for the spin 1 representation. You can get J plus and minus for the spin 3/2. You can get, I fixed it here. I don't know what happened. You can get J plus and minus for the 5/2 representation. And I guess just, you have to churn out the Clebsch-Gordon coefficients, but those coefficients end up being these off-diagonal numbers here. So I guess what I was trying to say is that there is a mechanical way to figure out what all the matrices are. Like basically, as I said, the Z matrix is really easy. It's just diagonal. And then there's a mechanical way you just churn through the Clebsch-Gordon coefficients, and you can get the X and Y matrices as well. I would never want to do it, but I guess you can do it. I think I don't know why I put that there. That doesn't seem like it belongs there. And then so, oh, I remember. So I said that this was 2 copies of SU2. I think that comes back here because when we're dealing with spinors in spacetime, all these matrices were the SU2, right? These were representations of SU2. So if we want representations of SO13, we can break it down into 2 SU2 representations. So there's like the 0, 0 representation, which is just that's just like the 0 matrix. But then we could say for one of the SU2s, we want the spin 1/2 representation. So that's like those 1/2 sigma matrices. And that would be like we could say one of the SU2s is a spin 1/2 and one of the SU2s is a 0. So that would be a valid representation of SO1. Or we could say the first SU2 is 0 and the second SU2 is a spin 1/2. That gives us another representation of SO13. So basically you could pick different spin values for the 2 copies of SU2 and you can build different representations of SO13. I think these ones are the main important ones, are the Weyl spinors and the vector representation. But in theory, you can go as high as you want. And basically, this is the spin for SU2, the first SU2, and then that's the spin for the other SU2. So they're labeled D, J, K. Basically. I don't know if that's confusing people. This confused me at first. I had no idea what these 2 things were, but they're basically just, you have 2 copies of SU2, and you can have a spin J representation for the first one, and a spin K representation for the second one. And you can basically tensor product those representations together to get representations of SO13.
That makes sense. I don't know any physical interpretation of that, though. That's rather confusing.
Yeah, I don't, because the thing is, the normal representation of this is like rotations and boosts on a 4-dimensional vector.
Yeah.
That's the 1/2, 1/2, which is this one. So this is the one everyone's probably used to. But I guess if you study quantum field theory, you want to do left and right hand Weyl spinors. You want to know how those transform under Lorentz transformations, and those will transform under these representations. So they each get 1 copy of SU2.
So you decompose the space to work with it better, and the Weyl bases and everything else. Which actually does make sense now, because each Weyl spinor has a left and right chiral part to it, and
so I think one of them will transform with a U, and then the other will transform with a U dagger. I think someone can feel free to correct me on that if I'm wrong. Because vectors transform with the two-sided transformation, but that's the spin 1 representation where you have 2 copies of SU2 in the spin 1/2 rep.
because really you can see the basis as kind of different ways of compounding the main elements of the algebra, right? Because if you look at the gamma matrices, for example, they're really just the representations of the pseudoscalars, is it called? The elements of the SO31 algebra right there. The gamma 0, 1, 2, 3, 4. 4, no, not 4.
I'm not sure I followed you there. In the this is the Clifford algebra for this is CL 1-3.
Yeah.
And then sorry, go ahead.
No, continue.
Well, I was just gonna say the spin 1-3, which is the double cover of SO13. To get the generators for that, we look to these different representations. And I guess like Vial Spinors are 2 components because they're just a spin 1/2 representation of SU2. And the two Vial Spinors together give you 4 components, which transform under the standard SO13 representation, I guess.
Yeah. Oh, that makes sense. Thanks.
So yeah, I think that's it. So that was 2.5 hours. So that was a lot. I don't know if anyone actually left because they couldn't handle it anymore, but I guess that's all I have to say about Spinors. Yeah, so basically all of those, like in physics, I guess, you can have like a 2-component spinor that will transform under SU2. You can have, and I think like a vector in space-time can somehow be written as like the tensor product of 2 spinors, I think. I forget exactly how this works. And like basically each one would transform with SU2. So that's why a vector in space-time transforms like that. This is like the Pauli matrix, Pauli vector interpretation. Okay. Anyone have anything to say, or any questions?
Thanks for the lecture. It was good.
Yeah, I mean, it sounded like it sounded like Tim already knew most of this.
Yeah, bits and pieces. I don't know any of the physics.
Yeah, I might ask you. I don't remember when you joined, but I've had this question out. If I might go back here to the start.
Sure.
So, if I said that spinors can have like 4 different index types, there's like the contravariant, covariant, dot, covariant dot. Does that sound familiar to you, or is that like new?
I don't know anything about this notation.
Okay, never mind. No question to ask then.
I only know that it is called van der Waarden notation. And I have seen also that only in Physics from Symmetry book, and that's it.
Yeah, there's a Wikipedia article on van der Waarden notation, but it doesn't explain it very well, in my opinion.
Mm-hmm.
Van der Waarden.
I wonder if it's in my book. I can quickly skim it.
Because like they show like 2 of them, I think. Like they. Oh no, this is not what I want. Van der Waarden notation.
How do you spell it? Okay.
Yeah, so like here it's saying like a left chiral spinor is like a covariant index, and a right chiral spinor is a contravariant dotted index. And then the Dirac conjugate, I guess, is a contravariant and a covariant dot. I don't know what this means. I've been trying to figure out what they all mean. I had this theory that when we were talking about mathematical ideals, that like these, I'm going to delete all the ink because it's in the way. But my theory was that like this is where the contravariant components lived. This is the contravariant dotted components. This is the covariant components. And then this was the covariant dotted components. That was my theory. I'm going to be try and prove that that's true over the next few weeks, or find someone who claims that this is true. This is my suspicion.
Could you pull up the wiki page for the notation?
Yeah.
Just really
sure.
quickly so I can skim it?
Yeah.
I mean, I guess I can pull it up on my phone. If you want to look at something else.
I'll just paste it in the chat quickly.
Oh, awesome. There's a lot of the stuff to do with the like near the end of what you were talking about. There's a section in representations of compactly groups by Berker. Part 2, section 10. I wrote it in chat if anyone cares. That goes through that construction completely. It's really good.
The construction of what? Sorry, the compact.
Well, it's stuff to do with like the raising and lowering operators.
Oh, okay.
That stuff.
Okay, I will go to that. That was Brocker Part 2, Section 10. Okay, thank you.
Yeah, there is a photo of the book in channel.
I think the previous section as well is pretty good.
Okay, I will take a look at that.
Yeah. So what was I doing? I was looking at the thing you shared. I'm just going to read this.
Was it so, Chris, that for ideals they were really the minimal ideals also?
Yeah, I think these are minimal ideals, at least in the 2x2 case. Yeah.
If you wish, I can ask it from my doctor friend. So if I send this picture to him and ask if he can take a look and answer in English.
Yeah. Maybe I will give you two pictures to show. The first one it actually defines what all of these matrices are, so I'll send this one into the chat.
What was the question? I didn't hear it, sorry.
Yeah, so it's about the dotted and the non-dotted indices. I'm wondering if those come from what we call ideals in matrices. There's like 4 ideals that come up that I just posted.
Well, it's probably going to be related to irreducible representations of the spin group on the Clifford algebra, something like that. And it's probably going to split into 4 pieces. It just means that all that irreducible representation means, so like if you have like a rotation matrix, standard rotation matrix, acting on like R3, so 3-dimensional rotation stuff, it just means that if you have some vector in that space, that it can be taken to any other space. Basically, if you have some group action, so some matrix that that kind of mixes everything up, so that the way that it acts on the whole vector space keeps everything within. Like if you have some subspace that everything sort of gets rotated and stays within. So like say if there was a plane in R3 that that all of the 3-dimensional rotation happened to keep all of the vectors within that plane, in that plane after a rotation. You know that isn't the case because you can always rotate kind of up out of the plane into the 3rd dimension. So we say that like as a 3-dimensional representation of SO3, the standard matrix stuff is irreducible because it kind of takes everything everywhere. But if you have oh god, what's an example of something that would be reducible? If you have an abelian Lie group, so if you have a circle, the circle group is just the unit complex number. You can represent them on like higher dimensional complex, on a higher dimensional complex vector space, like say C2, by just rotating everything by some constant. You'll have 2 subspaces of C2 that everything sort of gets kept within. And so that representation splits into those 2 irreducible representations. And then so with Clifford algebras, a vector space, the reason that they're minimal left ideals is because you have like the Clifford algebra, the spin group of the elements of spin group are also elements of the Clifford algebra. So you just hit everything in the Clifford algebra by the elements of the spin group, and it'll split into pieces because it's a subgroup, because it's not the whole thing. And
right,
I think in mixed metric you'll probably have more pieces, and that's probably where you have these like why you have 4. I think with the normal, like if it's not mixed, so more boring case, not as related to physics. I believe it'll split into two pieces. Well, it depends on the dimension, I guess. I think anyway, it's not important.
Like this whole splitting into 4 pieces, I think it happens for spinors of any dimension. I don't think it's just tied down to like SO13 or something like that. I think this is like universal for all spinors.
Yeah, but in Penrose's book, he says that it's not true. So it happens only for even dimension.
Oh, yeah. Okay, even dimensions. Okay.
Yeah. I don't know why, but I seen that in the book.
It's because in full jargon, it's because the homomorphism into the endomorphism algebra of that Clifford algebra doesn't split in odd dimension. It has in even dimensions it preserves parity of the even and the odd parts, but in the odd dimensions it doesn't. It kind of everything gets jumbled up in the odd cases. But with the even ones, it keeps like the even ones even and the odd ones odd, sort of. So you have those kind of discrete bits, the subspaces that sort of stay within their own realm. And I think with mixed metric, you're going to have more of those because mixed metric is weird. And you get crazy extra pieces happening. I think that's why, if I had to guess.
I'm going to have to keep reading about this, but okay.
Yeah, well, feel free to ask any questions if anything comes up. I only know maths. And even then, I only learned this like a couple of weeks ago.
Tim, do you, or are you a member of any group here on these Discord server or not? Beta or
alpha? Of the book club?
Yeah.
Server? I'm a member of all of the groups. I think I'm an admin of the group. Great.
I just was thinking where I can find you if I forgot your nickname.
Yeah. I think I've got my DMs kind of disabled, but I can adjust that a bit if need be. People send me messages, spammy things that I turned off. But yeah. I mean, I'm pretty hard to get hold of for the most part. Brandon and Brooke will attest to that. But,
wanted to ask you one small question. I've been rereading a few times, or a lot of times actually, the Wikipedia page about spinors, and it seems like I only understand their definition or their line of thought in there on like basic level. But what I have seen in there is that they're saying that like spinor spaces are kind of the representation of a spin groups, which do not factor out through that like exact sequence standard for SO3, which kind of includes SO3. So it kind of means that spinors are kind of the objects which have the memory of the homotopy class of the past, right? Or something.
Yeah. So you have there's a name for it. I think it's genuine. Okay, so because SON is isomorphic to a subgroup of spin n, every representation of SON can be pulled up by just saying, but it can be pulled up to a representation of spin n by just basically, as Chris was saying, you can sort of identify the negative plus or minus one in the spin group. At the
so you can blow up it into like kind of fiber bundle. You can add plus or minus one.
And it becomes completely boring because the like these representations are boring as spin representations because the negative one element behaves exactly the same as the identity element in the spin group if you pull it up, because it kind of SON doesn't contain the information, treat them any differently. But when you have what's called a genuine spin representation, it's the other way around. So you have a representation of the spin group, which you can then restrict to a representation of SON. It kind of goes the other way, right? Instead of pulling it up, you kind of push it down, and you get one on SON for free, but you also get one, like you get more information upstairs. And as far as I'm aware, when you have an irreducible representation, an irreducible genuine representation, the spin group, then elements of that representation, which are elements of the automorphism group of some vector space, those correspond to spinors. At least in the definitions that I've seen. Although it seems to be that word is attached to a lot of things, because there's also, I think, spin fields, like the sections of spin bundles. They're also called spinors, which I don't know anything about. I
have a random question. Like when people talk about a vector field, vector fields aren't too hard. You just like put a vector at every point. I've heard that spinor fields are like harder or weirder to make, and you need like sections of fiber bundles. Do you know if anything I said is just true, and if it's true, why it's true? Okay.
Yeah. So when you have the more formal way to think about a vector field, you're right that you just attach a vector at every point. But the way that we do it in, say, differential geometry, more so, is to look at the tangent space of the manifold at every point. You just look at all of the tangent spaces. We call it the tangent bundle, which is just like you have your manifold, and then attached to every point is its tangent space. And so if you have any point in this space, it's like it's a vector with sort of memory of which spot on the manifold it is an element of the tangent space of, something like that. And so a section of this bundle just means, or a smooth section in particular, smooth vector fields, means like a smooth assignment of a vector to every point. And the way that we do this is that with vector bundles, tangent bundle, with fiber bundles in general, you have the total space, which is just the whole bundle, and then a map to the base space, which is just the manifold. So the map from the tangent bundle to the manifold itself is just forget the tangent vector, or forget the tangent spaces. And so a section is just a map that if you do, and then it's a map from the manifold, from the base up into the bundle to the total space, such that if you do the projection afterwards, it's the identity, which just means that you've assigned one thing up and then gotten rid of it. Pretty much all that means. Now, with spinor fields, as far as I'm aware, are you familiar with the concept of a principal bundle?
No. So like everything you said about tangent bundles made sense to me.
Okay.
But I don't know what a principal bundle is.
I think principal bundle is when you have like a symmetry in your tangent space or vector space in there. So you have like some group assigned.
The simplest principal bundles are like if you have a Lie group and you have a normal subgroup of it, it forms a principal bundle. If you're familiar with the group theory, it kind of just happens to be this way. It tends to be easier to think about. So like if you have SON plus 1 and SON, if you quotient out SON from SON plus 1, the result is a sphere. You end up getting, this is sort of how the Hopf vibration comes about, just in a special case of this sort of thing. But basically it's just you have a manifold, and then as your fiber, it's a Lie group that behaves a certain way, pretty much. Such that the quotient is, lots of smoothness, lots of compatibility. It's anyway, it's not important.
So in principal bundle, you have like a smooth group attached as a fiber.
Yes. the fiber is isomorphic to the group. The fiber isn't actually a group, but it's isomorphic to a group, or diffeomorphic to it. It's a technicality, but it's important, because like the stuff that you do in you don't, because otherwise you sort of have identity elements in your principal bundle which you don't have. It would give you extra information that you don't have. Otherwise, it's complicated. But yeah.
Those are used in gauge theories, actually. Yeah.
Yes. This is the gauge group is one of these groups. It's you have some space where some manifold where if you quotient out a Lie group structure, which is some symmetry, you get the base space. And so I think for you have like Spacetime as your base space, and then you have gauge groups. Was SO, it's SU3 cross SU2 cross U1 gauge groups for standard models, something like that. It's just a Lie group. Now spin fields. That's what we're building to do. So over any Riemannian manifold, you have you can construct what's called the frame bundle, which is over every single point you have the tangent space, and then over every tangent space you have like all of the possible basis vectors. And without the Riemannian metric, you can do this for any smooth manifold, or any manifold really. And the structure group is GLN, just the dimension of the tangent spaces, changes of basis. But when you have a Riemannian metric, you can restrict this to the orthogonal ones, just the ones that preserve the metric at each tangent space.
So you are saying that tangent bundle is principal GLN bundle?
What the frame bundle is, it's directly related. You can create what's called the frame bundle. So you have your base space, and then over every point you have all of the possible changes of basis of the tangent space at that point, which is like having GLN attached at every single point of your manifold. And then when you have a Riemannian metric, you got your inner product, so you can restrict to orthogonal transformations. And then you can restrict further to orientation preserving transformations if your manifold is oriented, if your bundle is orientable, whatever that means, if you're unfamiliar. And then that restricts the group so we've restricted it from GLN down to ON, and then to orientation preserving, it's down to SON. And SON is familiar to everybody who was just talking about spin groups, because the spin group is the double cover of SON. So you form the spinor bundle by just taking the double cover, pretty much, and then looking at a representation of the spin group. There's an extra condition that is required. So in order to go from ON to SON, you needed to have that the bundle was orientable, which is the first Stiefel-Whitney class, corresponds to this. Its value. It has to vanish. In order to go from SON to spin N, which is sort of the next kind of looping, next kind of rotation level sort of stuff, you need the second Stiefel-Whitney class to vanish, which is more complicated. It's not as easily thought about, but it's some topological invariant of your base space that has to go away in the same way that it has to be orientable to preserve an orientation. And then you have this crazy space, your manifold with your spin group structure. Then you form what's called an associated bundle. You represent at every point, instead of having the group, you represent the group as a vector, like on a vector space, and sort of swap it out, such that the representation smoothly varies around as you go around the manifold. Then sections of this bundle are spin fields. After all of that, that's what spin fields are. Yeah.
So, what's the reason you can't just say put a spinor at every point? Is there is there a problem you run into where you need all this extra baggage?
Because a spinor, at least as far as I'm aware, formally, is an operation on a specific kind of vector space. So in order for you to do that, you need it also describes a certain kind of symmetry, and not all manifolds have this symmetry. So you can't, because a spinor isn't actually a vector. It operates on vectors, like a linear transformation, sort of. It's just kind of more general in a way. So sort of what you end up with a spin field is you have like these vectors from the representation stuck to every point, but these vectors behave very, very nicely with respect to the spin group action in a way that because spin group has to, the whole point is to use its symmetry, and you kind of can't. You can't just stick a vector on and hit it with a spin group and call it a spin field. The vector itself has to be, it has to be a representation of the group in the first place in order for the group to act on it. And for various topological reasons, things break. When you try to do it over every manifold, you need to have this extra condition. This Seipel-Whitney classes, blah blah blah.
It sounds like I have a lot of reading to do.
I know nothing about the Seipel-Whitney classes outside of this. Like everything that I just said is all I know about the topic because I haven't done anything about it. It's like I'm only just learning about like I only learned most of this stuff a couple of weeks ago. So yeah.
There is an interesting video on YouTube by Atya, and he's giving a lecture about spinors. And he's talking a lot in there about works of Donaldson, about four-dimensional like topology and differential geometry, and also Vitan, Zeinberg invariance and all of those stuff. And so, like from point of like higher grade mathematician, spinors are really usable in those like higher matters.
Yeah.
I think I saw that video, and he started off by saying, "I'll explain spinors in a way that even you can understand." And I like didn't understand any of it, and I got
it was so hard.
Yeah, but it starts off deceptively easy, and then it skyrockets really fast.
Actually, that video, you shouldn't lose the context. You should take a look to whom he is talking at. And he's talking to like really high-end specialists, like Misha Gromov is in there, specialist in hyperbolic geometry, and he's kind of genius. And you're like, okay, okay, it's fine that I don't understand that.
I wish I got to meet Atya before he died. It's really sad. He died. I think he died in 2019.
Atya.
Unfortunate. Yeah. And Singer died this year, I think.
Yeah. This year.
Early this year, or yeah.
Yeah, it's
very sad. All these giants.
Could somebody link to that video where he's describing the spinors?
Yeah. I will send you a link now. Yeah, to the beta chat.
It's kind of like a survey of work relating to them. It's unbelievably difficult to understand. Like outside of the first like 20 minutes, maybe or less. It's just unreasonably dense after a point.
Yeah.
Yeah. God. Cool.
I've sent a link to beta chat.
Thank you.
At some point, I might try turning all these talks I've given into like a spinor tutorial for normal people who are not all these people you just talked about. But I probably won't do that this year. Maybe next year when I understand all this better.
The idea is definitely interesting. I'm concerned about like what is required to get kind of the full picture, or like any picture, because it's not easy. I mean, as you've seen, things get kind of wild, and it uses a lot of maths.
You're talking about spinor fields, right?
Well, no, just spinors, any of it. It's complicated.
Well, yeah, I mean, I would start with probably just spinor algebra before you go to spinor fields. I assume would be the right way to do it. But
yeah. But I mean, as sort of I apologize if I interrupted you a bit much. I didn't mean to throw you or anything. I was just,
No, I think it's good to have someone who knows what they're talking about, because I think most of us in this call don't really know what we're talking about.
I mean, that's nothing wrong with that. I mean, if this conversation was happening, I don't know, a month ago, I would be in the same boat. I just happened to just be learning this stuff. That's all. So it's convenient. I got lucky, basically.
Maybe you can recommend some book about the principal bundles stuff you've been talking about, or some kind of source.
So there are two books that I worked through over the course of about a month. It's Representations of Compact Lie Groups by Broecker, and Compact Lie Groups by Stefanski. I think in general, no, not in general, maybe beta chat. I took a bunch of pictures from the Stefanski book, from just the Clifford algebra section, where it's defined and explained. It gives the isomorphism with the exterior algebra. This kind of thing defines the spin group and the pin group. Just it's formal. It's dense, but it is the complete picture. And then from Broecker's Representations of Compact Lie Groups, it covers a lot of the stuff that's kind of underlying the machinery of things that were mentioned. Sort of in the stuff to do with the spherical harmonics is like an explicit determination. But in the book, it shows that all of the irreducible representations of SU2, of SU2, are related to the spherical harmonics, just of various dimensions. And then from the stuff to do with SL2C, with the raising and lowering operators, you get a bunch of differential equations and these crazy polynomials, the spherical harmonics. They come out as solutions of these equations. It covers a lot of this ground, and it's I think the first chapter is like all of the prereq knowledge. So it would be good to work through the first part of Broecker. It'll run through a lot of the the basic group theory of these Lie groups, manifold stuff, the topological arguments, some differential geometry, lots of these things. It sort of runs through all of the basic stuff before it dives into representation theory. I believe there's a chunk on homogeneous spaces, which is principal bundles of special homogeneous spaces. I think to do with transitive actions. I think they've just got a bunch of extra properties. It's pretty good. It's a good book. The exercises are necessary. It's hard. But it's really cool. It's really cool stuff.
I've heard somewhere, I don't remember where, but I've heard that this thin, really subtle, double covering nature of SU2 and SO3 and spinors are kind of the gates to the real higher mathematics, and it seems like a black hole, or how to describe that. It's kind of really sucking you in, and you kind of can get out, you suck everything while researching spinors.
Well, the crazy thing is, it touches on a lot of areas of mathematics. straight out of the gate, a Lie group is defined as a smooth manifold with a group structure. You need to know what a group is. You need to know what smooth manifolds are. You need to know how to translate the two. And then you have matrix groups. You need to make sure that your linear algebra is pretty on point. You need to make sure that your calculus is on point because of differential geometry stuff. And then you start talking about double covers and universal covers, and suddenly you're talking about topology, algebraic topology in particular, because the stuff to do with simply connectedness, really it means that its fundamental group is trivial. It's empty. And the reason that you have this craziness with the SON groups is the fundamental group is Z mod 2, the integers mod 2, cyclic group of order 2. And from algebraic topology, the fundamental group of a space corresponds to deck transformations of its universal covering, which is to do with like automorphisms of the covering. And so with Z2, it just means like it's the parity swap, which is like the plus and minus 1 in the spin group being mapped to the same point. So it's like jumping up or down a layer. That's what that corresponds to. So you're dealing with algebraic topology. And then when you start talking about representations, it gets really heavy into like polynomial algebra. If you stuff to do with the theorem of Peter and Weil, that's all functional analysis. So it's a whole other area of maths. And stuff to do with like the classes of like isomorphism classes of irreducible representation, starts talking about category theory, and other things to do with representative functions is algebraic geometry. It's all of it. It covers everything. All areas of mathematics are involved with this stuff. So like it's just insane. It's like it's easy to approach in chunks. I've found to like try to do all of the things that pertain massively to one area of maths, and try to learn that, and then realize that I can't progress. Go learn more maths, and then come back to it. I spent a couple of months cramming algebra so that I could finally start dealing with these books. But it's really hard. It's really hard. But it's good fun, though.
Yeah, I believe you.
So, sorry, I might have misheard you. Did you say there was a section of a textbook that talked about the dotted indices, or was that...
I don't think that was me.
No, okay. I might have misunderstood something you said, but that's fine.
Yeah.
Okay.
I thought also the same. That Tim said something about that.
Yeah. I think you might have been talking about something else, like representations.
Yeah, probably that's true, yeah.
Honestly, that dotted index stuff is the thing I'm most curious about, because that's
about,
like the tensor.
About lowering, Tim, about lowering the spinor index.
Okay, what I'm going to do is quickly, I'm going to look at, I'm just going to flick through one of these books, look at the index, just to see if I can,
well, because there's I've seen a few sources talk about a spinor metric, and I pasted it just a few comments above here. Let me get a better.
Well, I assume that that's just going to be a metric that's it's an inner product that's invariant under spin action.
Yeah, it's kind of like a symplectic inner product. It's
what is the symplectic inner product?
Let me just
weird
take.
What? So it's in like not because with complex you have Hermitian, and with the quaternionic you have skew Hermitian. But it's like that, but generalized up to the spin groups. Is that?
Well, I just posted in the beta chat like this for the two component spinners. Spin metric is just this matrix here. I think.
Let's have a look. I think I know where it might be in this book. So I'm just going to quickly skim it and see if I can pick it up. Because I think the spin invariant metric is going to be related to any, or at least compact Baker group. You have the killing form. I believe it's going to be related. It's not exactly related, but it's. I don't think it's exactly the same thing, but it will be related because it's an inner product that either left or right or both invariant with respect to the group action. But I don't know about spin groups. Do with it. Let's have a look.
Yeah, I propose to do some planning for the next call next Saturday. It seems we finished with Spinors for some time and need to kind of think more on the material we got from Chris. So thank you so much, Chris, for your work for the previous months.
Yeah, well, I mean, I wanted to learn it too, but I am a bit tired and I don't really want to make any more talks for a while.
Yeah, it's understandable.
I'll be a contributor, but not a leader, I don't think.
It's understandable, totally. So I propose, first of all, to go back to the Road to Reality book. So let's finish chapter 25 the next time. And maybe prepare some questions. You can refresh all other subsections we have already discussed in chapter 25. And so we will talk...
What stuff is covered in chapter 25?
A standard model.
Oh shit! Okay, yeah, you're gonna start talking about spin fields.
Yeah, so standard model. We talked about like basic weak forces, Zitter-Bevegun model for particles, or like zigzag model. So, and why weak forces are not symmetric due to the parity transformation, mirror transformation.
The weak force is which symmetry group is that? SU2?
Yeah.
Okay, shit.
Yeah, so they have
it's in a week, right?
Yeah.
I was gonna say, Road to Reality definitely leaves out details. Like, it gives you like the bare minimum, and sometimes not even the bare minimum. Honestly.
Yeah, that's true. So,
right.
Yeah, to understand standard model, we need to work a lot harder and a lot more. But currently, we just focused on passing through the Road to Reality, and afterwards we will see. Like we can go further and deeper into the branches.
Very, very nice. Something that I've found, especially stuff relating to the Lie groups. So I don't know, maybe about a week ago, I got into an argument with some of my friends who were studying physics, like who were like they're about to do a quantum mechanics. It's that time of the year here. And they were sort of, they didn't really they were sort of mocking what I was doing because they didn't really know what I was doing. And so as a point, I tried to learn how to answer like a chunk of this stuff. And it just comes for free. If you learn the math, the physics just sort of happen. So the stuff to do with the quantum harmonic oscillators, I didn't know anything about until about a week ago. And it's just because it's just attaching names to mathematical concepts that I already know. So like really like invest in the maths. It kind of, everything else sort of comes for free.
Yeah, and that's why
the most efficient way to spend time.
We are studying Road to Reality here because it's like physics book from a mathematician. That's I think one of the main reasons.
Tim, you seem to have quite a lot of background. If you get it all in 2 weeks, that didn't happen to me.
Well, I spent like 6 months studying algebra. So I got my algebraic foundations nailed down. I spent all of last year learning just basic, well, no, maybe not basic, but some algebraic, elementary algebraic topology and differential geometry, tensor calculus, blah, blah, blah. So really, I worked, I kind of fucked my grades. So I finished my second year of undergrad last year. And now I decided that uni is kind of too slow. So I'm at home studying. Because I fucked my grades last year, spending all my time learning things, which is hilarious. But, I spent all my time doing it. So it's not like I'm not anything special. It's just all that I do. So it better pay off or I'm fucked. I don't know if that makes sense.
As it made sense. Yeah, we've been talking about the differential geometry and all these studies. We should have a really good background and basic studies from there and build up.
Yeah, and
sounds like that.
Also, Tim, we have a YouTube channel with recordings, so I can share a link with you, or just feel free, you can write to me and I will share.
Yeah, sick. If things work out, I might be able to sort of help with things. I might be able to give a talk every now and then. I'm hard to get a hold of. I don't spend a lot of time near electronics. It's hard to get a hold of me. But I mean, if you send Brooke or Brandon a message, they'll pass things on to me. It tends to be the easiest way to get a hold of me. But I'd be happy to give a lecture every now and then if it's on something that I know anything about.
Yeah, sounds good.
Helps anyway.
Speaking of YouTube, do people have a problem with me directing people to that video? I know some people are recorded, they might be self-conscious about that, but is that fine if I point people to watch it?
What today recordings involved with that?
Yeah, I don't know if you're okay with that. I think a bunch of other people said they would be, but I don't want to invade people's privacy if they don't like the fact that they're being recorded.
Yeah, and we do not have any nicknames on the recording, today's recording, for example. We have only screen with the slides and voices.
I'm not really fussed. Doesn't really matter. Yeah, no.
And still okay to me.
Okay, yeah. All right.
Yeah, sure.
I just wanted to remind...
This has been on Rogan. It's not going to matter much.
I wanted to remind everyone here...
Going to happen, already would have.
Yeah, sorry. I just wanted to remind everyone that Marco, his nickname is Mesocosmos here. He wanted to make a small also presentation of his home experiment going, or ongoing experiment.
Ooh.
Yeah, with gamma rays or something, yeah. Marco.
Holy shit.
Oh, yes. So I posted those presentation. There's a PowerPoint presentation and the article for the case study, and then also an essay. So there's a lot of material. I was thinking, I'm doing this experiment and being advised by the original inventor of the experiment. So I still don't have these exotic power supplies. So I'm waiting for those until I can myself replicate the experiment. Once there's a presentation that should give all the information that's related and how you can get some overview to the experiment. So the question, it was just that if people want me to present this overall presentation, or if people want to get to the presentation when I have done my. So that was the question.
Yeah. Yeah. So Marco, do you want to take some time from the call next week, or?
Yeah. If it's okay to people, yeah.
Yeah, it's good with me.
Yeah, so basically we have only 2 subchapters from chapter 25, so I think we can review those quickly, and afterwards you can go on and just present your material. So.
Okay.
And that
it's point 7 and point 8 in the chapter.
Yeah, 7 and 8. Yeah, 7 and 8. Yeah, and
okay.
And then we will continue with your presentation.
Okay, I will link those documents again, because they are quite far behind now, so people can take a look at those. Or is there any other way?
Yeah, I will make an announcement about our plans for the next week. Maybe today, maybe tomorrow.
Yeah. Then it's okay.
What I'm gonna do is I'm gonna send you a friend request, just so that you can send me a DM should you feel inclined to, because I have my DMs turned off.
Yeah.
So otherwise I won't be able to get them. That would it'll also be the easiest way for you to get my attention. Because like I said, I'm not around a lot. Chris, I can't. It's not going to let me add you as a friend. It says that I can't send you a friend request.
Do I have a privacy thing turned on? I don't know. I don't know how Discord works.
I think so.
Let me check my settings.
It says that you might have to add me, but I can't add you.
Okay, maybe I'll try adding you. Okay, it says I sent a friend request.
Awesome.
Okay.
Cool. Yeah.
I don't know how Discord works.
If there's anything that I can help with to do with the spin stuff, like with the math side of things, just send me a message. I'll help where I can.
All right, thanks.
Keep in mind, I don't have a degree of any kind. I'm no one, so take what I say with a grain of salt. But I don't think I'm wrong with some of this stuff.
The degree doesn't matter actually if you got some clockwork engineering in your head going on something.
Sure. Yeah. Well,
after all, many of us are just self-learning here. Some people are in the schools and so forth, but not everyone.
Oh, awesome. My people then. Yeah, I don't want to pretend to be something that I'm not. So I'm just no false advertising coming.
Yeah, don't worry about that. We will try to filter out or to help you to understand things better with our feedback if we can.
Sick. Well, yeah, a lot of the physics I really know nothing about. So I should probably be attending these regularly, just to get more perspective on a lot of things. Would be helpful.
Yeah, we'll be really glad to see you again here.
Hey, that's kind. Nice of you.
I actually need to go now. It's quite late here, so I just want to tell thanks, Chris, and I will ask this thing from my friend and send you some message if I get something.
Sure. Yeah.
Yeah.
This has been our longest call ever. Sorry.
Yeah, I don't recall when it was so long. Yeah.
Slava, is it 5 a.m. for you now?
No. It's 11 p.m. 11 p.m.
Okay. Okay.
I'm just gonna quietly not say that it's 6 a.m.
Oh no! How are you this like mentally active?
You're a night person also,
I'm nocturnal. I'm a travesty.
Okay.
It's just this is how I work. I'm a mess. Yeah.
Yeah, me too. I know how it is.
Yes. Best.
All right. Well, I will catch you all next week then. Thanks.
Yeah. See you.
Go recover, Chris. You worked hard. Go chill.
Thanks. All right. Bye. Take care.
Yeah. Have a nice week. Bye.
See you, everybody.
Take care.